Good morning, sir.
Good morning.
Speaker joined? I don't think so.
Mm-mm.
Rajesh is there. Rajesh did not join. So, Nilesh, you are handling the session, right?
Yes, ma'am.
Yeah. So, for this lecture, you prepare a briefing. For rest of the lecture, I'll ask Rajesh to prepare the briefing.
Okay, sir. Okay.
Good morning, Professor Bhattacharya.
Good morning.
Speaker joined.
Good morning.
Good morning. So, you are able to switch on your camera?
Yeah. Just sorry, I forgot that. I'm sorry about that. Yeah, so my camera is switched on now. I'll just
Yeah, yeah, that's
reduce
good.
the
Yeah,
background.
we are able to see you now.
Yes, sorry. Yes.
Good morning. Good morning, Dr. Bhattacharya.
Good morning, Dr. Milind.
Yes, thank you.
Yeah, good morning.
So I can see our colleague, Dr. Om over there, among
Yeah,
others.
Doctor.
So, okay, Dr. Aruna Tiwari, good morning.
Yeah, good morning.
And then I think the first time we are seeing each other.
Yeah.
Dr. Milind, I think we have met somewhere. I'm not able to recall.
Is it? Probably, yeah.
Anyway, that's all right.
Let's start the session, Nilesh.
Yes, ma'am. Good morning to everyone. I welcome you all to the third third day of the workshop, HPC workshop. We have the 2 days previous. We had 2 previous days with great eminent speakers talking about the cultural HPC work. We had 2 days very eminent speakers talking about the various research domains in agricultural domain. For the today's theme, we have HP high performance computing theme, and we have the very first speaker with us, Dr. Professor R.K. Bhattacharya. Ma'am, would you like to please introduce Dr. R.K. Bhattacharya, sir? Neha, hello, Neha, ma'am. Now, I would like Neha, ma'am, to please introduce our very first speaker, Dr. Professor R.K. Bhattacharya, sir.
I think we're not able to hear anybody other than Dr. Nilesh.
Uh,
Yeah, now I am audible.
Yes.
Sir, are you able to hear me, sir? Okay.
Yeah, it is audible from my side,
Dr.
right?
Neha,
Yes, now it is audible.
Yeah,
In between, it had gone.
yeah. So let's start the session. Welcome, Professor. I'd like to introduce Dr. Ari Kumar Bhattacharya is the Dean of Research and Professor of Computer Science at Mahindra University. He has been with him more than 20 years of industrial experience, including at Defense Research and Development Organization, ADA Bangalore, Alstom Transport UK, and at Tata Steel Automation Division, Jamshedpur, all in research and development roles at different levels. He has been AICT INAE Distinguished Visiting Professor at Birla Institute of Technology, Mesra. Professor Arya has filed for more than 20 patents and published more than 40 papers in journals, international conferences, and book chapters. His multidisciplinary research interests over artificial intelligence, machine learning, deep learning, evolutionary algorithms, game theory, and autonomous systems applied to different domains like aerospace, manufacturing and industry, logistics, supply chains, transportation, and others. His title of the talk is Design of Hybrid CPU-GPU Architecture Parameters Enabling Training of CNNs, Convolutional Neural Networks with Evolutionary Optimization. So now floor is with you now, Dr. Bhattacharya, please.
Thank you, Dr. Aruna, for this nice introduction. So I will start sharing my screen. So I'll just request you to tell me once that the screen is
Sure.
visible.
Yes, this is visible.
Okay, thank you very much.
You can make it full screen if possible.
Yes, I will make it full screen. I am getting a little this
Yeah.
thing at the. Yes, I think I have.
Yes, it is full screen now.
Right. Thank you very much.
Yeah,
So,
let's start.
good morning to all of you. So, like this is, I'm actually going to speak on some work that we had done with, I had done along with some of my young friends in most of last year. So this is actually design of hybrid CPU GPU architecture parameters enabling training of CNNs with evolutionary optimization. So this is me, of course, and these are the other authors. So we have got one student who is a master student from École Centrale Lille, that is in France. Then we have got two others who are our own students, Rochen and Janavi. Okay, so I think I'll proceed now. So the outline of my talk goes approximately like this. So first I will, although I understand that this is the topic is of course high performance computing, and I'll definitely come to that. But I'll start with the potential significance of training artificial neural network parameters using evolutionary algorithms. So number of times we'll have ANN and CNN as acronyms. So ANN I just now spoke, and CNN is convolutional neural networks. Then there are two bottlenecks in doing this. One is the humongous amount of computation, and two is matching backpropagation for accuracy of course, results. Then we'll talk about the design of HPC architecture that breaks through the first bottleneck. And then we'll talk of evolutionary algorithms, particularly differential evolution with local search, that achieve the desired accuracy. and conclusions and future work. Okay, so let's start off. I would just like to say that normally in such workshops or conferences, we have the questions at the end. However, if someone feels very seriously that there is a need to ask something, please feel free to go ahead. Stop me and go ahead. Okay. Now, backpropagation. So we are taking a deviation into artificial neural nets to start with. And like as I think most of us or all of us are aware that backpropagation has been the workhorse and has now so much of a workhorse that it has now become almost a paradigm of deep learning. So this essentially applies steepest gradient descent to engage in local search. So this is an illustration of a typical conventional fully connected feed-forward ANN. So you have got, I presume my cursor is visible. So we have got in this particular thing, one input layer, one output layer, and there are two hidden layers being shown with some number of nodes or neurons. So what happens is that in this we have the propagation, the backpropagation propagates the error backwards from output layer based on the error levels towards the input layer, modulating each weight, that is the weights of the parameters, along the way in proportion to the sensitivity of the error to each weight. So this is just just a schematic view. So the dark lines are showing the forward progress of calculations, and the dashed blue lines are showing how the error is being propagated backwards and modulating the connecting weights along the path. Now, evolutionary algorithms have a completely different way of doing parameter training, just as evolutionary algorithms are quite different from gradient-based approaches generally for optimization. So evolutionary algorithms that traverse over the global search space without taking into consideration the underlying architectural landscape. So what this implies is, again, the same architecture. So we have now picked up some, we are actually pointing out at some locations or connecting weights A, B, and C at quite different regions of the architecture. So as you can see, A is actually just the pre-final layer connecting weights, B is intermediate, and C is input to the first hidden layer. However, the connecting weight parameters A, B, or C are treated exactly similar in the process of training. That is, the weights are treated in a neutral to position in architecture manner, or you can say that it is a kind of agnostic towards the location and direction of the propagation signals. All right, every weight parameter is treated as a similar variable of optimization. So this is the way they work. EAs work concurrently on a population of candidate solutions. Ballpark can be anywhere between 50 to 300, and hence are computationally more intensive. Very roughly, n times a backpropagation solution, where n is the number of candidates. So if there are 100 candidates, we would expect that EA to take about 100 times more computation, or you could say computing time, as compared to a typical backpropagation solution. And now I use the phrase very roughly. So this just gives a ballpark comparison. Now, this is where we get into something different. So there are certain accepted facets or the way we interpret deep learning. So we'll just get to deep learning is just back. You can probably say it's, it's a concentric circle within machine learning. And of course, it predominantly deals with ANNs. So when we are dealing with particularly image recognition, or rather image classification, so we have the image given as the input layer. So if you consider the layers going from, or the flow of, sorry about this, flow of control going from left to right, then we have the image at the leftmost layer, which is the input layer. And then let's say the first activation layer will just pick up the edges. Okay, it basically picks up the lowest level features. And then it starts assimilating or putting together the higher level features. So if you look at it that way, so we have the image at the extreme left, which is not shown here. Then you have edges, which are being picked up. Then you have textures being picked up. Then you have patterns in those textures. Then you'll start seeing parts. And finally, you will start seeing the object. This is the point where you have the softmax, which is recognizing or giving a probability of certain objects. That is where we classify the original image. So this is actually, I think one can appreciate that if, this is the way it works. So basically, it is a hierarchical build-up of features across the layers as one goes from the input to the output layer. Now the question is, okay, so I just already stated this, low-level features from activation maps close to input layer to high-level features next to final layers. But then we should not forget that the way we have trained is that we have taken the error at the final layer and gradually propagated the error backwards, modulating the weights along the path. All right. So is this itself not a consequence of the fact that we are identifying the error in the object at the final layer and gradually modulating the weights to align with this while traveling towards the initial layer? That is, can we not say that this hierarchical recognition of features of an image is itself a consequence of the method of training, that is backpropagation? Now, the thing is that a lot of things, a lot of aspects or facets of deep learning are associated with this hierarchical buildup of features across layers. So there are some other facets intrinsically accepted as characteristics of deep learning, which can be considered as manifestations of the underlying backpropagation paradigm. So one of these are, I mean, a lot of people nowadays, actually, it is very important issue, this issue of explainability or interpretability of like whatever is the output from ANN or CNN or RNN or whatever. So explainability or interpretability aspects mostly work on the assumption of hierarchical evolution of features across layers. Then the high sensitivity of image classification or object recognition to specific input pixels can be traced to paths of high sensitivity, that is gradients across layers. Now this is again associated with the method of training, that is backpropagation. Then the vanishing and exploding gradient problem is well known, which has led to the evolution of architectures of the LSTM family. And this again, we can very easily appreciate is a result of the steepest gradient method. All right. So now if the local gradient descent, that is backpropagation, is replaced by global optimization performed by evolutionary algorithms, then what will be the likely impact on these commonly accepted characteristics or facets of deep learning? So this is a question that we are asking. Hierarchical evolution of features across layers is most likely to change, but then the question arises, in what manner will these features evolve or transform between layers? We do not know that. What will be its impact on interpretability and sensitivity of recognition of objects to input pixels? How will the vanishing and exploding gradient problem work out? So these investigations are likely to have a profound impact on the field of deep learning. But these investigations can be proceeded with only if two crucial advances are achieved on evolutionary algorithm-based training of parameters of deep architectures. So what are these two requirements? Or what are these two crucial advances? Now, the first relates to computing speeds, as we just now talked about a little while earlier. So EA-based training is expected to take about NX more computing time as compared to BP-based training of identical architectures with, of course, the same datasets and activation functions, where N is the number of candidates in the population. Now, this is a rough approximation. The second assumption is that EA-trained networks can generate similar or very closely comparable accuracy levels as BP-trained networks for identical architectures, activation functions, and data sets. So only if we are able to achieve these two, will we be able to get into the kind of relook at the entire way in which images are interpreted and the corresponding issues related to sensitivity, vanishing gradients, explainability, and things like that. Now we have successfully achieved the first and obtained speedups of between 100x to 400x for training of ANNs of variant architectures using evolutionary algorithm. So this effectively brings this kind of comparison, that is training of weight parameters using EA within the domain of practical application. We discuss this in the next few slides, and that is where we relate to this workshop also, that is high performance computing. Sorry. Further, we present comparative accuracies achieved on regression and image classification MNIST problems. Of course, the image classification for MNIST problems trained using differential evolution, enhanced with local search versus trained with BP. And here also we will show that we have actually been able, through the results, will show that we have been able to, and this is also a bit of a breakthrough because so far that was not really working out that way, that evolutionary algorithms can generate accuracies of similar levels as that can be achieved using backpropagation. Okay, so let's proceed further. So let's look at the way in which we try to speed up the computations for evolutionary optimization. So when we do evolutionary optimization, there are actually two levels of parallelism. So what we call as the outer level or the optimization phase. Now, this is where we are actually talking of looking at, let's say, as I said, we have evolutionary algorithms and they work on a population of candidates. So let's say we have 100 or 200 candidates. And then in principle, these 200 candidates could be launched on different computing, threads or CPUs or things like that. So that means basically they're on different computing channels. So here, what we call as the outer optimization phase, one of the most important things that is relevant for evolutionary optimization is that the candidates have to pass information across each other. So in this, even though they're launched on different channels or different threads, there's a good deal of need of transfer of information across the computing agents. On the other hand, when we go for the, when I'm looking at any candidate, any particular individual candidate, I have to evaluate the fitness of the candidate. To evaluate the fitness of the candidate, again, now coming back in this particular context of ANNs, sorry, we will have to look at, we'll have to put a whole lot of data samples in forward pass, evaluate the error, and that error is going to give us how accurate is the particular set of weights, which are the parameters corresponding to that particular candidate. And this actually, evaluating a large number of samples through forward pass, involves massive number crunching, but with very little need for broadcast of information across the computing agents, except for transfer of information between the candidate and the particular object, the object evaluation program or the agent. So this is the inner level, this forward pass for objective function. So in principle, we can have parallelization here. In principle, we can have parallelization here. So the first thing that we had done in this context was that we carried out something called as profiling. I think all of you will be aware of profiling. So we were actually working on NVIDIA DGX1 supercomputer with 220 core CPU and 8 NVIDIA Tesla V100. I think, 8 NVIDIA Tesla V100 cards. So in the profiling results, the profiling basically tells us that which part of the program is occupying what percentage of the total time. So here, what we are referring to as baseline is actually just running on one CPU. So when we carried out the calculations on one CPU, we found that the calculation of the objective function takes 96% of the time. And then the other operations in the evolutionary algorithm, crossover and mutation, each take less than 1% of the time. And the total time per epoch, now by epoch we mean we are training the ANN or CNN, whatever. In fact, this is for CNN, was 268 seconds. Now, when we go to, now this is just for a CPU. So then when we actually combined a CPU and a GPU and then carried out the bulk of the objective function evaluation on the GPU, then we found that, okay, I should actually mention, look at the total time also. So here we have of the order of 1293. And then for the objective function evaluation, crossover was 0.497, mutation was 0.2. And then when we look at the single CPU GPU calculation, objective function falls by a factor of almost, you can say, 3 orders of magnitude. Whereas crossover and mutation don't really improve much, but then to some extent also. But we find that in place of that, there's a good deal of time being taken up in the transfer of data. And so while the total time has fallen from 268 to 34, now the bulk of the time is going for transfers and the other calculations are taking much less time. Okay, so that means we have to, if we can work at this point, if we are using single GPU, CPU, GPU, we have to work on the transfers, point number one. And point number two, we'll also have to see that instead of a single GPU, since we've got a number of GPUs, so how do we actually put them all together, all the CPUs and all the GPUs together? So basically, the problem one was suboptimal parallelization. So we have to have an optimal scatter strategy for parallelization across GPUs and suboptimal heterogeneous communication and optimal gather strategy for parallelization. So when you talk of scatter or gather, it's basically information or data. An optimal gather strategy for parallelization across CPUs. So partition strategy. So what did we do? So, like if we take the typical path, that means we have the, say the candidates distributed across CPUs and the objective functions passed on to GPUs. Then each CPU communicates with each GPU and then correspondingly there's an oversaturated bandwidth. Now, if we do it only on GPUs, then we have problems related to synchronization and like which CPU is communicating with which GPU, and also the GPUs need to communicate with each other. So we actually combined these two aspects and created what we call as the best strategy, where we have got each GPU tagged on to a CPU. And then what is really happening is that almost all the data transfers are occurring at the CPU's level. Between GPUs, there's absolutely no data transfer. The CPU information is being transferred to the GPU for. So that means basically there are candidates launched on the CPUs. The CPU carry out the higher level parallelization or the higher level evolutionary optimization tasks like crossover and mutation, whereas it passes the information to the GPU for carrying out the objective function. And then this is actually, so we have got a mapping of GPUs to CPUs so that we don't have cross CPU-GPU communications. So this is the approach that we have kind of developed and followed through. So in essence, parallelism is implemented at two levels across population candidates by loading them onto different CPUs. And the cost function evaluation of each candidate, I'll just bypass the bracket part, and the cost function evaluation of each candidate on GPUs that are coupled with corresponding CPUs running the candidate whose cost function is being evaluated. So when we say cost function evaluation, what we really do is we forward pass through thousands of training samples and evaluating net errors. The cost function evaluation of each candidate is basically on GPUs that are coupled with the corresponding CPUs on which the particular candidate is running, whose cost function is being evaluated. So this is the approach that we have followed. And actually, like, we have sort of, this is actually testing that we have done on the MNIST problem, which has got about 60,000 training samples. And we have used actually, one is the typical conventional feed-forward fully connected ANN, and another we have used a CNN. Now I'll talk more about the CNN architecture down the line because it has got some special characteristic. Particularly, we have completely removed the pre-final fully connected layer. So this has got about 11,250 parameters, and this has got only 6740 parameters, which looks pretty small for a CNN. But then you have to keep in mind that the bulk of the parameters blow up in the fully connected final layers. So now, in the first set, we have actually carried out a number of calculations. So we have got one CPU. Then we have got 6 CPUs in parallel. Then we have got one CPU and GPU. And finally, we have got 6 CPU-GPU combinations. And the training time has actually come down from 273 to 56 to 5 to 3. So we have got recently we published a paper also on this in the CEC 2021, where we have more detailed calculations on this, but I'll not get into that. So here now, when we go into CNNs, it actually takes much more time. And in fact, there are reasons why CNNs take more time than ANNs, although the number of parameters are less. So here we have got something like 12,436 seconds. And then it comes down to almost a factor of 6, 5.5 or something. And in fact, that's true here also. So the factors are more or less holding across this. Then we come down to 172, and finally it comes down to 33. So if we compare the factor, it is about 371x. I mean, in 6 CPU GPUs, we have got about, say, 400 odd times faster than we had on a single CPU. So speed is attained on CNN and ANN, 371x and 88x respectively, when number of candidates is 200. Okay, so if the dimension of the solutions, okay, now you see, before I get into this, so this is about the CPU, this is about the speed up part. Now next I'll take a deviation and look at the other aspect, which is basically related to the accuracy levels of the results generated using differential evolution with local search. Now, in the differential evolution local search, we have actually again developed, I mean, in the sense there are some algorithms already there, and then we modified those algorithms. But I would not like to get into this because then I'll greatly overshoot the total time. So I'll just bypass these slides. So the first slide was talking about differential evolution. Then there's about local crossover and there's about local mutation. I will bypass this, but if someone is keen, we can come back and talk about this again. Now let me come back to the issue of comparative performance of ANNs and CNNs trained with DE and local search versus trained with backpropagation. So for making this comparison, now as I said, if you just go back with we said there are 2 essential points which you have to verify, or which are 2 essential advances that we have to make before we can carry out those calculations, which are essential to evaluate alternative paradigms of training of ANNs. That is basically the evolutionary algorithm paradigm and its impact on the various aspects related to, say, the feature recognition across layers and all that. So the first was speed up, which we have seen. The second was that for the same data sets, for the same activation functions, obviously for the same architectures, we have to compare BP accuracy versus EA accuracy. So that is what we are doing now. So we have taken 3 cases for these comparisons. 2 regression problems using field acquired noisy industrial data. I'll just talk about this. And 1 classification problem, that is the MNIST problem. So regression problems handled with classical fully connected feed-forward ANN architectures. We didn't go into CNNs for this. Classification problems handled with both feed-forward ANNs and CNNs. Now both are trained using BP and DE. When we say DE, DE enhanced with local search. For BP, standard available libraries are used. DE is based on the algorithms outlined in prior slides, which we have not really seen, for which libraries are unavailable, and we have to codify all that. Okay. Comparisons performed across same architectures, activation functions, and data sets, including the splits of data sets. That is, even the splits were kept similar. Splits means across training and validation. Next few slides present these comparisons. So the first, we have regression problem 1, where we have prediction from noisy industrial data on skin pass mill. That is the final link in the steel manufacturing process chain. Now, this again is something which will take a little bit of time to give the high level view. So I'll just try to say that what really happens, like when you talk of steel manufacturing, there's a chain of processes starting right from the mines. Then we have the generation of liquid iron, then conversion of liquid iron to liquid steel, then conversion of liquid steel to solid steel, and then formation of sheets. And then they're also called as strips. And then they pass through what is called as various mills. Now, in these rolling mills, what really happens is, like you have things like wheels, which are fixed actually on their axis, and you have the steel coming in, the steel sheet coming in, and then there's a gap. So it actually has to align itself to the gap. So essentially what happens is, the width is ensured to be the same, the thickness is reduced, and as a consequence, the length goes up. Now, this is done at various stages. So the very last stage before the steel is sent to the customer is what you call as skin pass mill. So I'll not go further into this. So we have used actually 13 inputs for the ANN, which include, one of them is the percentage elongation. Just now we talked about elongation induced by the skin pass mill. And then the other inputs are basically various kinds of inputs picked up from different stages, because as I said, there's a chain of processes. So we have things like temperature, we have things like chemical composition and various other things. The output is the yield strength, which is basically a mechanical property of the steel. So looking at these, now we are comparing here. One is what you see on the x-axis are generations. What you see on the y-axis is what you call as R-square values. Now R square, as you know, is a good method of comparing, say prediction versus actual. So R square is equal to 1 is the ideal situation where you have exactly 45-degree line passing through the origin. So here you have got DE and here you have got BP. So it seems DE is giving a better solution, but you have to keep in mind that the y-axis itself is, the spacing on the y-axis is not very large. So this is about R square of 0.835, this is about R square of 0.841 or something like that. Okay. So increase in accuracy expressed as R square values across generations for DE and BP. And in fact, when we have this is just the typical, what I was trying to talk about, the R square is something. So these are on the x-axis is the true values, y-axis is the predicted value from the ANN, and this is the kind of corresponding chart that we get. So now what we did was, in this particular case, the output was yield strength. The inputs were 13 parameters, which were 12 various parameters, and one of them was actually what we call as a skin pass mill elongation. Now we sort of transform the problem. See, ANNs have got the facility to do this when you use the database methods rather than domain-specific functions. So what we do is, at the next level, we actually we made the yield strength as one of the inputs and put the SPM elongation as one of the outputs. Now automatically this becomes a control problem, because here what we are saying is, given the other 12 inputs, if you want a certain yield strength, that is a certain mechanical property of the steel that is being produced, then what should be the SPM elongation that you should set your plant for? Okay, so I'll not get into all these hyperparameters at this point. So evolution, so here we have got the corresponding control of noisy industrial process, skin pass mill. Okay, fine. So in this particular case, we have got, again, generations on the x-axis, validation of R square value, and we have got Now, please remember this. I mean, I just forgot to mention this. This is not training set. This is the validation set. So again, compared to BPD is slightly better, but then as you can see, the scale of the x-axis is very large. So these intervals are spacings are indeed very small. All right. So now this is the corresponding true values versus prediction values. Now you would be expecting something like a scatter, but you find a little surprisingly that why there should be fixed values. The true values should always be at some fixed values. And that is because the true values are always at some given settings of the skin pus mill. So we have picked up the data from some existing settings. So these are what the true values are always not scattered like the previous one, but at some fixed values, and we have a line like this. But here the important thing is that we got R square of 0.97. If I just go back for a second, earlier we had R square of about 0.84. So from 84, we have got a very high this thing, 0.97, because here in the output value, there is no noise. It is a fixed value. So you can just understand that, when you have genuine industrial problems, or you can say any kind of practical application problems, how much noise impacts on the ability to learn. All right, I'll not get further into this. So now we get into MNIST classification. I think I've got still about 15 minutes if I'm not wrong. So MNIST classification. So here, the first thing we did was we used the ANN. But when I say ANN, I mean the conventional feed-forward ANN. So here, we are looking at accuracy evolution for MNIST classification ANN architecture trained with BP. So here we are comparing validation and training dataset for the ANN trained with backpropagation. And we find that, obviously, first of all, we have got, you'll find that the training data is little better than the validation data, which is absolutely expected. And we find that we have got accuracy levels of just above 0.95, or you can say 95% accuracy levels, which is not very great, because I think you are all aware that MNIST can be very close to 100% accuracy if you use the proper architectures and CNNs. Sorry. Now, for the same architecture, accuracy evolution for MNIST architecture, ANN architecture trained with DE. Now, in this case, I would just like to say, although because of the y-axis you're not able to say, but I have got the values written down here. So again, we have the validation error slightly less than training error, and the actual values are, let's look at the last part. Accuracies on validation datasets, BP has given 95.1% and DE has given 94.8%. So in the regression cases, we found that the ANN trained using differential evolution is actually giving slightly higher accuracy as compared to the ANN trained using backpropagation. Here we find that in this case, of course, this is for so far we have been dealing only with ANNs, not with CNNs. We find that the DE accuracy is slightly less than the BP level accuracy. Okay, then we have used the CNN. Now in this CNN, we have the important point to note is that the CNN architecture completely removes the fully connected pre-final layer. Thus, the first important point is significantly reducing the total number of weight parameters. Now, what really happens the reason why always in CNN architectures you are, I would say always, but most of the time, one keeps a fully connected pre-final layer, is that if you look at the trajectory of what we call as the influence of every input pixel onto every single output value is actually not ensured just by the filter mechanisms that we have across the activation maps. So that is why you have to have a final fully connected layer, which actually allows the influence of every single input to pass to every single output node. Now, when we remove that fully connected layer, first thing that happens is the number of parameters fall drastically, but at the same time, it is difficult to maintain the same level of accuracy that you had with the fully connected layers, for the final fully connected layer. Okay, so we have removed it because we wanted to deal with less number of parameters. Now, again, this is the same thing that we saw earlier, CNN architecture trained with backpropagation. And we have, again, validation, red line is validation, and the purple line is training. And when we now go for DE, we have similar kind of values, but I should actually state the actual values. So accuracies on validation datasets, BP has got 98.1% and DE has got 97.4%. Well, there are 2 points here. One is that one can always argue that BP should have given 100%, but then as I said, in that particular CNN, we have removed the fully connected layer. So possibly one could think of doing it differently, which would have increased the total, which could have given higher accuracy levels, but then it will also blow up the total number of parameters. The second thing that is noteworthy here is that DE has got less accuracy than BP. And you can see that one is 98.1%, is 97.4%. But here I would like to say that the algorithm that we have used, DE enhanced with local search, this 97.4% is the highest that I have seen so far in open reported literature of any evolutionary algorithm used for training the MNIST on any kind of CNN architectures. Okay, now let's go on to some other things which I just want to talk about here. So this was the baseline architecture which we had seen, 6740 parameters of CNN. So we tried to, without imposing a final fully connected layer, we wanted to experiment with different architectures. Now, even the different architectures are not very significantly different. So actually here, like we have got, you can actually see that there are 3 layers. And you have got actually now the layers of filters, first layer of filters, second layer of filters, third layer of filters. So number of filters, or what we call as kernels. So this was 3, 5, and 10. So first of, okay, anyway, so filter size, we have kept always squared. This was 7, 15, and 8. And we didn't have any 0 layer padding. So this is the characteristic of the 6740 parameters. Then we had alternative architectures where we actually increased the filter size. So as a consequence, we have 7, 11, and 12, the filter size. And this corresponds to 9180 parameters. And then we had actually taken further larger number of, filters of larger sizes. So this is called as heavier architecture. And the filter size is also 7, 11, and 18. And plus we had put some external 0 paddings. So as a consequence, the total number of parameters 21210. The lighter architecture which we had been talking about is having 6740, and the standard or the intermediate architecture is having 9180 parameters. Now the important thing is that what is the kind of results that we get when we compare these 3 architectural levels. So you can see the 3 architectures of light, medium, and heavy using BP and DE performance trainings. So this is using BP. So comparison of different levels of CNN architectures, MNIST trained with BP. And you see this is on the x-axis of generations, y-axis of validation accuracy. So you can see that the heavy architecture immediately gives higher accuracy as compared to standard architecture, and light architecture is the lowest, which is accuracy. So we see accuracy variation with number of parameters according to intuitive expectation, and accuracy increases with increasing number of parameters. So that is exactly what we expect intuitively. Now, what did we see when we used this on D? So here we see something which is quite strange. We find that the heavy architecture actually gives the lowest accuracy, and the light architecture gives the highest accuracy, and the intermediate architecture gives the intermediate accuracy. Okay, so accuracy seems to be highest at lowest number of parameters, and this goes against our intuitive expectation. So why? So what are the implications? So the profound implication is that optimization of architecture, hyperparameters, and weight parameters have to be done concurrently, all using an EA like our DE. So what I'm really trying to say here is that when we are actually using evolutionary algorithms for training, then the typical understanding which we have gained from before, that if you increase the number of layers, your accuracy is going to go up, need not be the case, because here our training process does not consider the local architectural considerations or local architectural aspects. And in fact, it is, as I said, location and direction agnostic in the training process. So then that actually making the requirement for always we need higher number of layers to get higher accuracies, which we have picked up since the days of ResNet, are not actually going to hold. And that is going to throw up completely new different paradigms once again. So now we have seen 2 different classes of paradigms associated with the backpropagation. One is that which is associated with basically the things like what we understand as hierarchical, you can say, learning of features across layers. So low-level features are picked up in the initial layers, then they assimilate, and higher-level features are picked up in the higher layers, and so on and so forth, which has got profound impact on sensitivity aspects, on explainability aspects, and on vanishing gradient aspects. Okay, so that paradigm can change completely if we use evolutionary algorithms for weight training. The second is the typically accepted paradigms that, if you increase the number of layers, then you're going to get higher and higher accuracy, or rather not increase the number of layers per se, but also increase the size of the filters, you'll get higher accuracy. That also may not hold. Okay, when we use direction and location agnostic evolutionary or global methods for training of the weight parameters. So to conclude, using concurrent task apportioning on hybrid CPU-GPU architectures, we have cut down computing times for evolutionary algorithms, or specifically DE enhanced with local search. So let me repeat the phrase. We have cut down computing times for EA-based training of CNN parameters by nearly 400x for population sizes of 200, thus bringing it within range of BP-based training range in terms of time. Using DE enhanced with local search, we have brought accuracies of EA-based ANN and CNN parameter training to similar levels as BP-based training for identical architectures and datasets. And then, now we are in a position to explore the different characteristic facets of deep learning, which we have conjectured to be implicit consequences of the BP training paradigm, using evolutionary algorithms, and anticipate possibly interesting interpretations and new perspectives. And we are also now in a position to explore neuroevolution, which is also very often referred to as neural architecture search. In fact, probably NAS is now a more popular term than neuroevolution. But then the difference is that neuroevolution always assumes that you're using evolutionary algorithms. Neural architecture search can be using anything. It can be using evolutionary algorithms. It can be using reinforcement learning. It can be using completely different methods or techniques for designing the architecture of ANNs. So let me repeat this. We are also now in a position to explore neuroevolution, where architectural aspects, hyperparameters, as well as weight parameters are all synthesized by EA-based algorithms. And this might throw up surprising revelations, which are counterintuitive to the longer plus wider is equal to higher accuracy paradigm that has got established post-ResNet. Okay, I think I will stop here. Thank you for your kind attention. So because I'm just got about 5 minutes left. So if there are any questions, I'm ready to answer. Shall I stop screen sharing, or is it all right?
Yeah, you can stop sharing, no problem.
Okay.
Sir, we have some questions in the chat box.
Okay. So chat
What are
box.
Yes, sir.
Okay,
Shall we read?
Shall we?
Yeah, I'm just reading these questions, so you will be comfortable.
Okay.
So one
fine.
of the participant, Shashank Sharma, question is, what are the advantages of evolutionary algorithm? Why go for EA if they are computationally more expensive and accuracies are also less than backpropagation?
So that is exactly what is the core idea of my talk. That yes, computation time is more, accuracy is less. I cannot really say because we have seen for regression the accuracies are better, classification they are less. Yes, but on the overall this thing is about the same. The reason is that whatever are the commonly accepted facets or aspects of say the learning, particularly in terms of interpretation of features across the layers, and the corresponding impacts on explainability and sensitivity and gradients or vanishing gradient aspects of training. So all these aspects are going to be completely, you can say, upset and removed or replaced by alternative paradigms if we have evolutionary algorithms. See, please don't, one can always ask that, okay, this is a typical question that one can always ask, that are you doing it more efficiently? When we say efficiently, the question is, are you taking less time? Are you getting higher accuracies? Now, if I say the answer is no to that, the obvious question is, why should we do it? The idea here is that in any scientific discovery, we also look at some different aspects. And here we are trying to see that we have got some established facets of deep learning, which could be quite different if the training is carried out using evolutionary algorithms, provided we are able to establish that we can get similar levels of timings and similar level of accuracies as in BP. So that is what we have got.
Yeah. Thank you. So there is one more question from Mitali Rai. What are the downside of using CNNs?
Okay. See, that's a question which can be asked to anybody. But like from my personal experience, I can say that CNNs are actually designed for images. All right, because you see, it essentially works on the local relation. See, if you have images, now if you just think for a moment, just think of an image of a cat, okay, and you've got pixels. So you are looking at a digital image of a cat. Now, if you just take out a few pixels from here and there and put them differently, the cat will vanish, right? So what it simply means is that the local relationships are very important in any image processing applications. And it's the CNNs which actually exploit these local relationships. And the whole idea of filters where we actually strengthen localized regions and try to understand or interpret the localized regions using filters or kernels. So that's the whole idea of CNNs. All right. Now, that is the advantage of CNNs in terms of interpreting images. However, there was a case where I showed you that when we are actually having 11,000 odd parameters on ANNs and 6,000 odd parameters on CNNs, the CNNs are still taking about a factor of, I would say, a factor of 6 more time as compared to ANNs. And that has got more to do with the method of parallelization or vectorization that is used in the high-level libraries for computation, where actually you've got a full matrix calculation for the ANNs because they are fully connected, whereas you have to actually traverse, where the filter has to traverse across the space of the activation map to the left, like it has traversed from left to right and top to bottom, and that actually takes up more time, basically. Okay, so this is the probably the downside of using CNNs as compared to fully connected ANNs.
Thank you, Professor. So next question is from Harshit Agrawal. Sir, can you please brief us on neuroevolution?
Well, neuroevolution is basically, you see, like, when we are, if you come to a CNN, let's say, or even a typical ANN architecture, usually the architecture is done heuristically. In the sense, you take a call on what should be the number of layers you're going to have. And then, like if it is going to be just a classical ANN, then the number of neurons that I would like to have across the hidden layers. If it is a CNN, then the filter sizes. See that then you have got blocks of filters. So the number of blocks of filters map into the number of activation maps to the right. Okay, and in each block, the number of filters is equal to the number of activation maps to the left. So all these characteristics that you do, you essentially do manually or heuristically based on some understanding that you have got. All right. Then the training itself is done using backpropagation. So neuroevolution, the heart of neuroevolution is that instead of using, you can say, heuristic methods for deciding on the architectures, as well as the hyperparameters that are used, so architectures and hyperparameters, instead of using heuristic understanding, why don't we put it into a mechanism where the training, where we automatically synthesize the architectures and the hyperparameters, which is going to give us the best possible accuracies in the least possible time. Now, even while doing this, so even while you are using, say, evolutionary algorithms for deciding on the architectures, that the core aspect of the training of the weight parameters can still be done using backpropagation. So even that is neuroevolution. What I have put across here is what you call as full or pure neuroevolution, where not only the architecture design, but also the synthesis of the weight parameters is also carried out by evolutionary algorithms. So that is what neuroevolution is in a nutshell.
Yeah. So thanks a lot.
Sir, I have one query.
Yeah.
Hello, sir. Are you
Yes,
able to hear
please.
me? Yes. So, sir, is there any method which give more better feature than CNN first 3 layer gives? So can we work for the first part of CNN rather than on second part? Or if we can propose the both new part?
Actually, I am not sure if I've understood your question fully, but just to remark on this, you see, even in the traditional
Yes.
CNNs, like if you look at AlexNet or even the later ones, they actually put the last 2 layers, or at least the last 1 layer, as fully connected layers. So when you have fully connected layer, it is
Yes.
almost like a typical ANN only. All right. So in these AlexNet onwards, most of the time they have put ANN-like structure at the very end, whereas the filters and all that are there towards the beginning. So it is more or less what you are saying. Only the first and second are interchanged. But the CNN that we have used here, we have not used any fully connected layers anywhere.
Okay.
So Any more
So,
questions?
but as a for a feature extraction, as for MNST, we are extracting feature of that image. Similarly, we apply for the cat or other if we have to classify. So,
Yes.
can we have better model which can generate better feature? Have you tried on that?
That is, see, like, when we say, I mean, if you say can we, the answer would be obviously that why not? We can always try. But in the context of neuroevolution, yes, because neuroevolution has got, like, in any typical evolutionary algorithm, in fact, you can think of either a single objective evolutionary algorithm or multi-objective evolutionary algorithm. So you'll have multiple objectives. One objective would be to minimize the total computation time, which is basically the total number of calculations or total number of operations, which is basically depending on what is the depth and the width of your architecture. All right. The other aspect, so basically one objective would be minimization of time. The other objective would be maximization of accuracy, or you can say minimization of error. So maximization of accuracy is a better way of looking at it. So you're actually having two objectives. One is maximization of accuracy, minimization of time. And if you try to work on this, then probably your question is going to be answered that yes, if the neural evolution is able to work completely, then this is going to give you better architectures with getting higher accuracies in lower times. Or something like a Pareto front. We have got one objective as time and the other objective as accuracy.
Thank you, sir.
Okay, so any
So I
more?
think there are no more questions. Thanks, Professor. Nilesh, please end the session.
Sir. Thank you, Arya sir. Thank you,
Thank you very
Professor
much.
Arya sir, for giving such a wonderful talk. Sir, your talk highlighted the points which is evolutionary algorithms for parameter learning, the various issues in backpropagation, and which kindly, like the problems of problems such as vanishing gradient problems, and which currently hold in the backpropagation, how we can replace it through evolutionary algorithms. And sir, you talked about the parallelism, like how can we use high performance computing parallelisms at the two levels, so that the accuracy and the time computation can be reduced. Sir, the three case studies which you involved give the good picturization of the differentiation between DE algorithms with local search with backpropagations, and it helped that really to give to get a better picture of how we can replace the big propagation algorithms with EA evolutionary algorithms. Sir, also the last point which you mentioned uh, about using evolutionary architectures, neuro architectures, which will give better accuracies than which are sure to give better accuracies than backpropagation algorithms. So thank you so much, sir, for this wonderful talk. Thank you so much.
Thank you. Welcome all the time. Thank you very much.
Thank you,
Thank you for your
Professor.
time, and thank you for giving me the opportunity also. Thank you.
Thank you, Professor Arya.
Okay, thank you very much.
So let's move to the next speaker. Nilesh, please.
Now I would like to welcome our new speaker for the talk, Professor.
He's from CDEC. He's from CDEC, not from Institute. So Mr. Ashish P. Kulkar, right?
Yes, ma'am. Now I would like to welcome our new speaker, Mr. Ashish P. Kolvekar, sir. And now I would like.
So welcome, Mr. Ashish. Aruna here. So my colleagues are there. You can see organizers. Aruna Tiwari here. Dr. Milind Parki.
Welcome, Dr. Gobekar.
Dr. Neha Bharil.
Welcome, Ashish Kulvekar, sir.
Dr. Om Prakash Patel.
Good morning, sir.
Nilesh is our
this workshop,
master's scholar
sir.
coordinating this whole session. Yes, so I think Neha is handling that session.
Yeah. Yes, ma'am.
Yeah.
Thank you, Dr. Tiwari. I would like to introduce Mr. Ashish Kulvekar before the start of the session. Mr. Ashish Kulvekar obtained his master's degree in electrical engineering from Vijay Technological Institute, Bombay University. He worked for 9 years with hardware R&D Division of Patni Computer Systems, Bombay, before joining Hardware Technology Development Group at CDEC, Pune. At CDEC, he has been involved in development of hardware subsystems for various generation of Param supercomputer systems and sharing knowledge with the students of PG diploma conducted by Advanced Computer Training School of CDEC. Currently, as a convener of NSM Expert Group on HR Development, he is involved in coordinating the activities of the expert group and implementing its mandate by working with various stakeholders from education institute and the industry. With this, I would like to hand over the session to Mr. Ashish Kulbekar, sir, and the floor is all yours, sir. I would request to please share your enlightening knowledge with all of us. Thank you.
Sir, you are not audible. Slides are visible. I think some network issue from his. Good morning, Amit ji. So today you spared time for attending the sessions.
Yeah, actually, we also having our event, so I was
Oh,
a little
yeah.
busy in that.
Yeah,
And
yeah.
since I think these are peak office times, so
Yeah,
uh,
I understand.
yeah,
So he rejoined, I guess, Mr. Ashish.
yeah, I think then there was a little bit technical issue, so I think
Yeah.
he got disconnected. So he's joining again. So we can see Ashish sir now, I think.
Yeah. Mr. Ashish, we are audible to you? Yeah, you are not audible. Still not audible. Not audible.
Okay, let me see there.
Yeah. So meanwhile, Om Prakash, can you announce for that feedback form when you are going to provide these feedback forms to participants? Would you like to make some announcement for
Ma'am,
feedback
it is already
forms?
Ma'am, it is already uploaded and announced in the YouTube chat. So participant, there is a feedback form is there on YouTube link description. You have to fill it for the certificate and the feedback of the workshop. Only after that you will get the certificate. It will take around 2 to 3 weeks to give you the certificate and preparation of it. So please fill it as early as possible.
So participants,
We
please,
will
because
keep
this is
it.
the last day. And, yeah. Yes, please, Om Prakash.
Yeah. We will keep it till 3:30 p.m. only. After that, we will remove from there. So please fill it.
Yeah,
Yes,
Amit,
ma'am. Over to you.
we were able to hear you.
Yeah. So
Yeah,
I
you're
think
audible.
there's a technical glitch in laptop. So I think sir is starting from the desktop. So he's just
Okay,
connected.
okay. Yeah, no issues.
So as participants, I can see Vikas, please stop it. I request please stop this. Yeah, thank you. So I can see as participants are writing in YouTube, we are not able to see the Google form. You can see in the description. We will not give in chat box. Just below the YouTube video you see, where the IIT Indore digital content is written, just below that there is a written feedback link is given below for the certificates. So you have to click that, then a new form will be open, then you have to fill that. I think please see
Participant,
it's
please, if
available
you
here
have any
because
concerns, please communicate with Dr. Om Prakash for this thing. But it is essential to fill the feedback form today itself, right? To avail the certificates.
if you put in chat box, then after some comment it will go up. It won't be visible to other. That's why we have given a description box. You can see easily. Ajay, I request you please in every 1 hour you can paste this link on chat box also. Is it fine? Ajay?
Ajay, are you there? Probably
Okay.
he went for
Ajay or
lunch.
Vikas, please come.
One by one, they are
Yes,
going
yes.
for lunch, na? So I think Ajay left for lunch. So Vikas,
Yes,
you
yes.
are there, I guess. Yeah.
Am I audible now, madam?
Yeah, you are clearly audible. Yes, please share
Okay. I
your
just
screen.
changed the computer. Sorry for the delay.
No
Are you able
worries.
to see the screen? Not yet. Okay.
Not yet.
Okay. Just a minute. Is it visible now?
Yeah.
Okay.
Visible.
Okay. I
Good.
apologize for this glitch and thank you, Amit. He also. Anyway, I was going to shift it to that. Just yesterday, I've used WebEx on it and it had worked. So that's the problem of technology. Anyway, so let's get going. I thank the organizers for inviting me for this talk. And this is as was explained by Dr. Neha, most of my experience has been in hardware development and architecture. So I will restrict my talk to those aspects of high performance computing, and hopefully you will find it useful in writing better parallel programs. So the title of the talk is how parallel computing at every level of the computing stacks helps us in achieving high performance computing. So this is the agenda, very short. I'll just describe the computing layers abstractions that we generally use and what are the parallelisms associated with each of those layers. So let's begin with what those layers are. So inside the hardware, the CPU that you use, I'm sure all of you know that you have execution units. These execution units, various types like ALUs, load store units, and floating point units, they together form what is called as a microarchitecture. So microarchitecture defines how a particular CPU is arranged. Like all of you would have heard about x86 architecture, and most of you would have used it. So x86, as you know, is a family of architectures starting with 80386 and right up to i3, i5, i7 that you use today. All of them are what is called as the x86 architecture. So if you would have seen how this Intel came out with newer and newer processors, what they did was they added microarchitectural features. As a result, the CPUs became faster, they had better capabilities, and so on. So that's what is the significance of the microarchitecture. So this together forms what is inside the CPU. So what we typically call as a hardware or a CPU or a processor or a socket. So that is what is inside that chip that you see with a possibly with a heat sink and a fan that you see if you have ever opened a computer. So that's where all this thing goes. So now here comes a layer which is called as the instruction set architecture. So the IA32 or IA64, that is instructions architecture 32-bit or instruction architecture 64-bit that we normally associate with Intel. So that defines how what are the, as the name suggests, what are the set of instructions that are there. They also define other architectural features like how many registers, what is the width of the register, and what capabilities does that processor have. So this instruction set architecture is an extremely important layer or interface that lies between hardware and software. So if you have studied any book on computer organization or architecture, much emphasis is given on this because this is in a way the specification of a processor. And once you have this, the upper layers, which include the operating system and the application programs, they make use of the hardware that is in a form of a chip or the CPU by making use of the facilities that are offered by the instruction set architecture. And of course, you have the operating system. We all know what it does. It allows the hardware to be used by one or more than one application program. So it acts like a broker between the application program that the user is using and the hardware that is underlying. So this is a generic way of uh, defining a computing layer, computing architecture with its different layers. So we are more interested in how parallelism is associated with these layers that we described in the previous slide. So as I mentioned, execution units are the ALUs and the load store units, the floating point units. So here, one feature that is typically used is what is called as pipelining. I'll explain each one of them in the slides to come. Then if you move to the microarchitectural level, there is something called as superscalar. So scalar and superscalar, what is this? I will explain uh, uh, next. Then many of you would have heard about this term, single instruction multiple data. Or if you have studied Flyn's classification, there are 4 ways the architecture can be classified. SIMD, or also called as vector instruction. So those instructions they give inherent parallelism to a new set of instructions that are available in those processors that use this SIMD architecture. When you move above to the operating system, you have things like multi-core. I'll explain what it is, how those cores are arranged, and the inherent architecture that any supercomputer uses. It makes use of multiple processors. So while the hardware offers these multiple cores and the multiple processors, it is up to the operating system to make sure that these additional cores or the additional processors that are available to us, they are being made use of properly, in the sense that the access to them is provided to the application program that is running on top of the operating system. So taking to the topmost layer, the application programming layer, here you have various parallel programming frameworks, and I'll explain a few of them in later part of my lecture. So let's move ahead. What is this pipelining? So we'll begin with an ALU. So as you know, it's an arithmetic logic unit, and arithmetic logic unit performs arithmetic operations like add, subtract, multiply, and logic operations like and, or, etc. So that is the basic unit which gives capability to any CPU. Now you have instructions, a set of instructions coming in that the ALU is executing as written by the programmer, and every instruction has its data to operate on. To give an example, you have plus or addition as the operation which is specified by the instruction, and that instruction will operate on data, which here are two operands whose value is 2 and 2, and the ALU produces the results, which is 4. So this is in the basic form. Any processor in the world, whether it is like for use for HPC or whether used for embedded system or the simplest of the processor that you can think of, all of them follow this basic method. And you have a program and a stored program, stored data, on which is a sequence of instructions operate on their respective data, and we get the results. So this also is called as the von Neumann architecture, and you must have heard about it. So this is what in a sequential manner the ALU keeps doing. So now when you have to expand this further, what I just now explained to you, you have a set of instructions. So if you break down the instruction, what it actually does, it typically does 4 things. First, the instruction is fetched. From where? From the program memory. Then one needs to find out what is that instruction supposed to do, whether it is add, subtract, multiply. So that is decoded to find out what it is, what is the programmer want the instruction to do. So it has to be decoded. Once it is decoded, we know that it is an AND instruction, like in the previous example. Then we will fetch the operands, execute it, and write back the results. So this is what a typical instruction cycle is, which takes 4 different things that it does: fetching, decoding, execution, and write back. So this can be looked in this form. If you look it on a time scale, that you have here one instruction. So in first clock period, or you will fetch the instruction, then you will decode it, then you will execute it, and then you'll write back. So that one instruction is complete. It takes 4 cycles. Next instruction takes 4 more cycles, and the last third instruction takes 4 more cycles. So in 12 cycles, you have executed, or the CPU has executed 4 instructions. So this is like what the earliest processor did. That when the processors were designed, they used to work. Okay, but now there is an improvement which is called as pipelining. So now what we have done is we have divided this execution cycle, as we already know, into 4 stages: fetch, decode, execute, and write back. So if you look at this instruction 1 and follow it, this is exactly same as before, that 4 cycle it takes: fetch, decode, execute, write back. Same thing happens here: fetch, decode, execute, write back, and it is taking 4 cycles. However, the change what we have done is, in the previous case, instruction 2's fetch was happening in the 4th clock. Instead of that, we have shifted it to T2 itself. Why? Because once fetch unit has fetched instruction 1, it is not doing anything. Why? Because instruction 1 then is given to the decode unit. Hence, we make use of the fetch unit here to fetch instruction 2. And in the next cycle, we will fetch instruction 3. So fetch unit is every clock cycle now is fetching instruction, not every 4th clock cycle, as was the case in a non-pipelined architecture. So thus what we are doing in, after an initial delay of 3 clocks, every clock you are getting one instruction executed. One from T4, T5, T6, instruction I1, I2 and I3, they finish execution. What was happening earlier? In T4, T8 and T12, instruction 1, 2 and 3 were respectively getting finished. So this is what the improvement that we have done, that by overlapping these kind of stages, we are able to take an instruction every clock instead of every 4th clock. And in this example, the number of stages are 4, so parallelism is 4. However, this cannot work smoothly if there are hazards, like there is a jump instruction. So if instruction I1 is at 100, location 100, I2 is 101, 102, like that, and if one of the instruction is jump 200, then obviously what is going to happen is the program counter is going to change from, let's say, 103 to 200. But the instructions are being fetched from consecutive location. So you may have to discard those instructions which were fetched, which are not going to be used. So what's happening, what we are trying to say is that this is not as smooth as it looks like. Sometimes we have hazards in the pipeline. So that is what is to be acknowledged. So point being made here is that pipelining allows you to have parallelism right at the execution unit level. So that was the parallelism at the lowest level. If you look at the microarchitecture level, we talked about what is called as superscalar. So what is shown here on the left hand side is the pipeline execution unit that we saw in the previous slide. So essentially what we are doing is we are executing one instruction per clock, and that's going on smoothly. Now what we do here is, when we have more transistors at our disposal and we can afford to add more logic inside the CPU, what we are doing is this execution unit, this is called as scalar execution unit, that is being duplicated inside the CPU. So instead of one execution unit, you have two execution unit. As a result, in the previous case, we had seen that only one instruction is fetched, one instruction is decoded, and one instruction is executed in a scalar unit. So only one single path. But when you have a superscalar unit, you have multiple paths. As a result, instead of taking one instruction at a time, we are taking two instructions and giving it to two units. Okay. So what is the result that we get? The instructions are sequentially written in the memory, but you pull out two instructions at a time, and as a result, you are able to execute two instructions in one clock cycle. So to elaborate it further, what happens is, in the program memory, from the program memory, you get these instructions in a sequential manner, I1, I2, I3, I4, like that. But what is the improvement that has happened? Instead of one ALU, you have two ALUs. So in the simplest form, what will happen is, the odd instructions will go on one ALU, the even instructions will be scheduled on another ALU. That's the way more than one instruction is being executed at the same time. However, just like we had a pipeline hazard because of jump instruction, here you could have similar hazards here if the instructions are interdependent. To give an example, suppose I3 is an instruction that depends upon I2. When we say depends upon I2 means, suppose I2 is generating a result. It's adding two numbers and generating a result. That's what I2 is doing. And I2 and I1 are independent. They are not having any operands common. So I1 goes on first ALU, I2 goes on second ALU. Now comes the turn of I3. Now I3 is using the result that I2 is generating. So I3 has dependency on I2. So I3 cannot be scheduled even though ALU1 is available until I2 produces the result, puts the result back in the registers, and only then I3 can be scheduled. If I3 cannot be scheduled, can I4 be scheduled? That depends upon the algorithm that is used inside the CPU. So point that is being made is there are some data and control dependencies which may prevent full throttle executions of instructions in parallel. All attempt is made to make sure that as many instructions can be scheduled together, 2 in this case. However, the dependencies have to be checked. So the golden rule that is normally followed in microarchitecture or any design is that you cannot have performance improvement at by compromising on accuracy. Accuracy is first thing that we need to look at. While maintaining accuracy, you can improve the performance. Okay, so that is how the superscalar execution works. So here we have shown 2 units. There could be 4 units, but as the number of units increase, the complexity of hardware design also increases. So that is the second level of parallelism, which is done inside the CPU. So please remember that both of these things that we do are inside the CPU, that is done by the hardware designers. Then comes the what parallelism we can have in the instruction side. So one of the things that is done is called as SIMD instruction. So as I mentioned earlier, SIMD stands for single instruction multiple data, and they are also called as AVX. AVX stands for advanced vector instruction. So this what is essentially done in this case by Intel and AMD, they added these instructions in x86 architecture, starting with I think the Pentium 2. Starting with Pentium 2, these instructions were available. So as you all know, these processors are 32-bit. Okay, the newer ones are 64-bit, but if you look at the 32-bit processors, they can operate on a 32-bit operand at a time. So the registers are 32-bit, the operands are 32-bit. But what we do here is that we increase the width to something like 512. So when we increase the width to 512, you are able to process 512 bits at a time. So now these 512 bits are partitioned. How are they partitioned? If you are using double precision arithmetic, then you are taking 32 of them together. If you are using single precision floating point, because now the width becomes half, you are able to process twice the number, that is 64 single precision floating point numbers can be operated upon together. Same thing happens for integer, because integers are represented using 8 bits and 16 bits. You are able to process more of them. So now what is the end result for the application programmer? Using these instructions, one can accelerate the workloads which are related to which domains? Scientific simulations, artificial intelligence like AI and deep learning, then image and audio video processing. So anything that has got what we call data, like video. What is video? Video is a collection of image frames. So same kind of transformation if you wish to do on a series of frames which is coming in a sequence, then this will be useful. At the architectural level, how it is handled, let me just explain. So this is the picture that I had shown you earlier, that you have ALU which works on a sequence of instruction. And suppose you have an array consisting of size 3 of 2 arrays, array A and array B, and you want to add the corresponding elements in array A to array B. If you were doing it on an ALU like this, you would have done it in the following manner. Take the first element from array A, take the first element from array B, add them together and generate a result which goes as the first element of array C. And if you want to add 3 such numbers, you will do it in sequence. And if you want to add 100 such numbers, you will create a loop which will be executed for 100 times, and you will be able to add those 100 numbers. Now, if you have a SIMD ALU, notice the difference. Instead of one data coming in at a time, you are getting 3 sets of data, in this case at a time. Now, the 3 instructions that you are using here, they collapse into a single instruction, because now if you notice here, you had 3 additions here, here is single addition. But what you have done, you have packed the data together. That's why that has happened. That has happened because you have this AVX which is wider. So the data path becomes wider, because of which you are able to take a set of data together. So in this example, there are 3. In the previous slide, I mentioned to you that you can have 8 of those or 64 of those. So this stack here will increase to, let's say, 8, 16, 32, depending upon what is the width that you have here. So to put it in a different way, this is how it looks like. A standard register of 386 or a 486 or a Pentium would be 32-bit wide. But when you have a SIMD registers, they are 128-bit wide. So in this case, suppose you are holding one floating point number here, then which is a single precision, then it's going to be 32-bit. But because now you have 128-bit registers, you can hold 4 of them, because 4 into 32 is 128. So imagine a thin line here, 3 thin lines here, because you are dividing it into 32-bit numbers. So the register, by increasing the register width, you are able to accommodate more data numbers in here. And depending upon what operation you are you doing single floating point operation, then you can hold 4. If you are doing double floating point, which is represented as 64-bit number, then you can do only 2. So this is how one can take advantage of the wider register paths, specifically when the instruction is same. Instruction is what? Add or whatever, or subtract. But the number of data that you are packing together is more. So from starting with Pentium 3, Intel introduced this, and now you have in i3, i5, and i7, you have more powerful instructions like AVX 512. So instead of it being 128-bit, in AVX 512, it is going to be 512 bits. Okay, so now those are the things that you do inside the CPU. So now let's see how does the parallelism come in, which the OS can exploit. So we saw 3 features earlier: pipelining, then we saw superscalar, and then we saw SIMD. So you take a CPU core, a modern CPU core that you are using today. It already has pipelining, it already has superscalar, and it incorporates SIMD instruction. So this is typically a CPU core which can take a stream of instruction which operates on a set of data, and it is able to process it. So this is our basic unit of computing. Now, when you take a multi-core CPU, even the mobile phone that you are using is likely to have 4 cores or 8 cores, depending upon what CPU it is being used in it. So here what we do is we take what we showed here, the entire CPU core, we take it and we duplicate it inside the CPU. This outer square is like a chip like this. So if you open this up, Intel Xeon, and see what is inside it, you will find in a particular implementation, you will find 2 cores. It could be 4 or 8 depending upon what chip you are using. So this is a core. It has got its own L1 cache, that's a private memory, and then they are connected together using L2 cache. And in this L2 cache then connects to the external bus. So when you are putting this on a motherboard, inside that chip, you are having more than 1 core. So now you can, in the simplest form, you can imagine that the operating system is running on one core and an application that you are running on another core. But in a real life situation, you will have OS plus many threads or many processes running simultaneously. So they are scheduled on these cores by the operating system. How that is done, we will have a quick look at that later. So this is like you have multiple core inside one CPU. Okay. If you take it further, let's say take a motherboard of a server which goes inside a box like this, and you see how that motherboard looks like. You will see two sockets, and these two sockets, each one of them will take one CPU. So if you have a motherboard with two sockets and each one of them has two cores, so you have 4 cores available on this motherboard. In real life, if you take a processor today, Intel processor today, is typically going to have 20 cores in one CPU. So you will have 40 cores on one motherboard. So if you take such a server and you at Linux, you give a command to find out how many logical processors are there, you will find something like 40 of them, 20 into 20. So this is now today, a node like this becomes a basic unit of computing that one can use. Now let's see how an OS handles it. So now if you take a simple thing like a very basic processor like Intel 88 that was there in the first computer, IBM PC computer that IBM made, then you will find that in this you will have only one processor, and the same processor is running the operating system like MS-DOS. Under that a program is running. So how does that work? If this is a time scale, the OS first loads, then you execute a program that becomes a process. That process transfers control back to the system because it's making a system call like printf or something like that. Then the control comes back to process 1, then it comes back to OS because the program 1 has or process 1 has finished execution. Again it loads. What does it load? It loads another program. So what you are finding here is that over a period of time, either the OS or a system call or a process is running. This is what happens when you have a very basic processor. But subsequently, what happens is that with faster processors or with processors with capabilities that allow multiple processes to run, in which case what happens is that you have something like a memory management unit. And when you have a memory management unit, multiple processes can stay in the memory, and you have a OS managing multiple processes running one after another on a single CPU. But in a real life situation, as I showed you here, if you notice here, you don't have one processor, but you have 20 of them or 40 of them, which a single OS has to handle. So what does that OS do? In that case, what the OS does is that it has got multiple CPUs, multiple cores. Now it takes as many processes are running, starts assigning to every core. So every core gets a process, and if the number of processes, let's say they are 40, but the processors are only 20, then there will be again time slicing as explained in the previous slide. So the job of the OS is to see what all hardware is available in terms of processes, cores, and the threads or the processes that are running, they are assigned to those processors. So like this, there is a parallelism that is achieved by the operating. And when you have a multiple processor, this is a generic way it is shown that you have processing element. Now this processing element could be a CPU with multiple cores, or in some cases, if you have a cluster, then this could be one computing unit, this could be another computing unit. So when you have a parallel computer, you obviously need to have multiple processing elements, and they have their own memory. We saw that the L1 cache that they have, that was a private memory. And then you have a bus kind of thing or some communication element which allows you to connect between them. So what we are seeing here is a parallelism at the multiple processor level. So you have multiple processors. So depending upon what architecture it is, you can model it as this could be the example that we saw here. In this case, the multiple number of cores were inside a CPU, or this can be extended to cores across the CPU, which are connected through external bus. So there are buses here, there are buses here, and here in this diagram, we have generalized it in such a way that we are calling it as some way of communication network, which binds all these processing elements together. So this is how in practice, you will see processing elements grouped together to form a parallel computer. Okay, so when you have such a parallel computer available, the next thing is to have how the application program can exploit the parallel computing elements that are made available by the hardware, which is managed by the OS. So for that, we have a few of them which I've listed here. OpenMP. So this is one kind of parallel programming framework that we have that works for shared memory computers. So it will not work when you have a cluster or you connect multiple nodes together, then it will not work. It will work only when you have a shared memory computer. So this is a compiler directive based. That means when you are using an Intel compiler, you give a directive that in that you put hash pragmas and say that this is the code that I want to parallelize, and the compiler will parallelize the code for you. So this works, as I said, for the shared memory computer. Then the next thing that you have is when you have a distributed memory computer. So what is a distributed memory computer? Like you have a cluster that in a lab, you have, let's say, 20 machines, and you have connected all the 20 machines together and using a network like Ethernet, fast Ethernet or InfiniBand. And each one of them is an autonomous computing element with its own memory, hard disk, etc. And you want to have a message passing between them, then you make use of what is called as MPI, or a message passing interface. And this is libraries. So you have to link the libraries, and you have to make use of a runtime environment through which the programs will run on the nodes inside the cluster. One of the newer frameworks that is coming up is called as OpenACC. So this is used with computers that have accelerators. So what is an accelerator? Many of you would have heard this term called as GPU, graphics processing units. So Intel makes them, NVIDIA makes them, AMD makes them. So these are additional add-on cards which have got chips from NVIDIA. Like you must have heard about these cards which are called as V100 Volta, or P100 Pascal 100, or the newer one is called as Ampere 100 A100. And in the previous lecture, the professor Arya had mentioned that he had used DGX1, which had got 8 GPUs. So these are the accelerators. So these accelerators help you, as the name suggests, in accelerating certain kind of workloads. And how do you make use of them? You need some framework. One of the frameworks is called as OpenACC. There is also another language called as OpenCL. So you need appropriate compilers which will help you in offloading the code that you're writing onto these accelerators. So that is the parallelism that you can. So this is what you can, as a programmer, you can exploit. So now, how I can tell in simple terms how you can, at the application level, how you can write or exploit parallelism or make use of HPC. So typically what you have is one main program which is called as a master program. Now that master program is going to spawn more processes through certain mechanism. What are those mechanism? One can use OpenMP, one can use MPI, or one can use OpenACC. These are some of the things that are available. There are few more things, like there are Python and which also can be used to achieve the same thing. But in broad terms, you can say that you have a program that will spawn these programs, and that's what you have to do in terms of distributing the processes to the processors that you have. Corresponding to that, you also need to give them the data, to which that code is going to work. So once you do that, this distribution of data and code, they can run independently. However, they can work independently to some extent. Once they have processed the data that you have given, they have to return the data. Like Professor Arya also mentioned about gathering the results. So that is what is that? Organizing the distribution and then synchronization by getting the data back. Now, while that is the part of the algorithm wherein you are simply distributing the data and the code to the processors that you have and making them work independently and then synchronizing their workflow, somewhere you have to also optimize the resource requirement. How? Through means of efficient algorithms. So one of the things that such algorithms do is what is called as compute and communication overlap, meaning distribution involves communication. Processing the data involves computing. And this can also go in parallel, meaning while you have distributed the data and that data is being worked on, the communication network is free. So what you can do is send the next data. When you send the next data, you are readying it for the next computation. So that is how you are going to optimize it by overlapping the computing and communication. So how do I summarize this? Parallelism is incorporated at every level of computing stack. We saw that in the at the microarchitecture level, at the execution units level, at the instruction set architecture level, and finally the programmer also can write parallel programs. The parallelism that has been incorporated inside the CPU, what we called as hardware, that is transparent to the application software. That means you don't have to worry about it. The hardware will take care of it because the program that you have written, it could be sequential, but inside the parallelism with control and data dependencies, it will make sure that the program is run faster. When the parallelism like SIMD instructions are part of instruction set architecture, so at that time, the compiler knows that SIMD instructions are present. It will check whether the user wants to exploit the parallelism, whether he has arrays, whether he has loops. Then that can be, instead of having a loop, that can be divided into by making use of SIMD instructions, the loop can be shortened because in one cycle you are operating, your program is operating on multiple data. So that is what the compiler handles. When you are using things like OpenMP, MPI, etc., then the user has to think parallel because traditionally we are used to thinking serial. Like when you get up in the morning, you say that I will do this first, then this, and that's how your day would be. That's what inherently we tend to think serially. But when you have a parallel hardware, at the algorithm level itself, you need to think about how you are going to design the algorithm so that you can make use of the parallelism that is available at the OS level, at the hardware level, so that your codes can run in a shorter time. So that's all I have in this short lecture, that in which what my aim was to make you aware of the parallelism that is available at various levels. Some of that you need not worry about as a programmer because the hardware designers will effectively take care of it. But when you have to make use of those features that instruction offers you, then the programmer has the choice of making use of them by appropriate programming techniques. So that ends my talk, and I am now open to taking questions. Okay. So
thanks, Mr. Ashish Kulvekar, for your wonderful talk. I would like.
Are there any questions?
Yeah, there are questions, Neha. It is in chat box.
Okay, I can see the chat box. What is the future of parallel? Yeah, is that the one?
Yeah, it is from Mithali Roy.
Yeah.
Neha, can you read, please?
Ma'am, actually, I'm unable to see in my chat box.
I
only
can see it. Don't worry.
Yeah.
Okay.
So I
I'll-
just let you know what is the future of parallel algorithm and its scopes.
Okay, so the future is as follows, in the sense that, as I mentioned, if you're talking about algorithms, then the algorithms have to be aware of the underlying hardware that you have, or the instructions or the features that are offered by the compiler. So when you are writing a parallel program, you have to think from the perspective of how that algorithm is going to be parallel. So if you do it from start doing it from that level, that thinking itself, that I will design an algorithm that is parallel in nature by exploiting the data parallelism or control parallelism that you have, then you are able to write a much better program. And talking about the scope that you are saying, that the answer would be as follows, that if you start thinking from the algorithm perspective and making it parallel, then you are in a better position to make use of the features that MPI or OpenMP offers, or a combination of that you can do. And the newer things that are coming up are like CUDA, that is the framework that NVIDIA is offering. And those architectures will give the programmer more better scope to not only to parallelize but to scale up. So when you parallelize something, then you should be able to scale up. You should be able to solve a bigger problem. So that is what the scope is going to be, that better and better hardwares are going to give you more parallelism incorporated in them, and you can make use of them. Okay. So that's the answer to the first question. Shall I read the second question? I can see it.
Yeah, no, I'll read.
Okay, please go ahead.
So Mr. Samantha is there. In parallel algorithm, as opposed to a traditional series algorithm, is an algorithm which can do multiple operations in a given time, and parallelism finds application in very diverse areas.
Yeah, it looks like it's more like a comment.
Yeah.
Yeah, I agree with him that parallel, that's what I was said while answering the previous question, that when you have the algorithm itself parallel, then that's the best thing to do. Because other option is that you already have a traditional serial algorithm, and then you find parallelism into it. But if there are some situations where you can inherently look for parallelism, like bioinformatics, etc. And I'm sure Amit is going to talk about it in his lecture in the second half. So there he will talk about exploiting those parallelism in the algorithm itself, like let's say search algorithm that you are doing, or in bioinformatics there are other algorithms that are used. So those will be those algorithms which inherently are parallel in nature, they will be able to scale up as well very well.
Yeah, I think it's done. There are no more questions.
Okay, thank you.
Any
and
other
sorry
question
for
from? No, it's okay. We made some useful announcement that time, and it was very useful because today is the last day.
Oh, okay.
So Neha, please end the session.
Yeah, thank you, Mr. Ashish Kulvekar, for accepting our invitation and giving the wonderful talk and sharing the aspects of the parallelism in the algorithms. This I would like to thank a lot to you.
Yeah, thank you. I will.
Thank you.
Thank you, Mr. Kulvekar. It was very informative.
Yeah, thank you, sir.
Thanks.
Now I would request Dr. Milind Bharti to kindly introduce our next speaker, Dr. Aruna Tiwari.
Hello, everyone. It's a great pleasure and honor for me to introduce Dr. Aruna Tiwari. Dr. Tiwari is working as an associate professor in computer science and engineering at IIT Indore. And she did her BTech, MTech, PhD in computer science and engineering from SGS ITS Indore. Dr. Tiwari has more than 20 years of research experience in artificial intelligence, machine learning, soft computing, and major focus has been on artificial neural network, fuzzy clustering, and their application to bioinformatics, medical diagnostics. Dr. Tiwari has more than 30 publications in national and international journals, including several of them in IIIT transactions and elsewhere journals, and more than 50 research articles in conferences, national and international conferences. Dr. Tiwari has also established a big data handling lab at IIT Indore, and which is funded by CSIR, and also had made several collaborations with different institutes and signed MOUs, including the Indian Institute of Soybean Research Indore and also CSIR Central Electronics Engineering Research Institute Pilani. And currently, Dr. Tiwari is leading several different projects on big data and their application is genomics. So we welcome Dr. Tiwari to this session.
Yeah, thank you, Dr. Ratnaparki, for introducing me. So slides are from, this talk, I am not the only person presenting because we are jointly working. Dr. Ratnaparki already briefed about the genomics area yesterday, and in fact, we are collaborating with each other since 2014, as I already briefed yesterday. Dr. Neha Bharil and Dr. Om Prakash, they are one more collaborating group from Mahindra University. So we planned that this talk jointly present. Me and Dr. Neha Bharil is jointly presenting this thing. So as the title of today's talk is Scalable Fuzzy Clustering and its application to genomics. And you know that this whole day is for high performance computing. So my more focus is on how genomics application we are taking to develop the algorithms which are scalable one. Mean how we can go ahead with the parallel computation over the number of resources available with us. So just now, Mr. Ashish, Senior Director from CDEC, already introduced about parallel computing, how useful it is. We have resources, but if we are not doing our task in parallel manner, we are not able to achieve the outcomes in faster manner and good performance. So that we have to plan. It's a big area of research nowadays due to the huge amount of data introduced and in fact keep on coming over the internet. And there is a need that whatever machine learning algorithms are designed, we have to make them scalable to improve the performance and to generate the output as early as possible. So that's the goal of this talk, that whatever we are doing, the target is obviously handling big data. It's not only specifically we started our research with genomics area. We started our research the work be to design the algorithms in which can be computed or perform learning in parallel manner a long back in 2013-14, and that time we was thinking that how we can handle the big data without thinking that how we can do with genomics. But now most of the problems we are dealing with the genomics as we got funding as well from various places. So the target of this talk is introduce about what are the genomics problem we are handling, how these problems are the clustering problem, because we are specifically targeting that how fuzzy clustering algorithm we made scalable, and in fact we are still working making few more innovations. So these are the two aspects, that designing of scalable clustering algorithms, and another goal is understanding the genome sequences which we are handling by collaborating with Dr. Ratnaparki from Indian Institute of Soybean Research Center in Indore. So please proceed with the next slide. So quickly, what is genome? As a lot of sessions have been yesterday on genome, but here I would like to highlight why this plant genomics problem we have taken is the clustering problem, because the target here is to focus on the computer science aspects of the genome data which we are going to handle. So you first understand why genome data we are taking as the data for the purpose of machine learning, right? So, genome, if we look at its sequence of some chemicals, like we call it as in protein case, we used to call it as amino acids, which are represented by these alphabets. So like you can see here, the sequence of alphabets on the right hand side, the sequence of alphabet like CTA or one line, another line, again, you can see the similar kind of alphabets, but in some sequence it is occurring. So the people who are not from genome side or bioinformatics side, they can quickly understand that genome or a protein is a sequence of alphabets. Now for computer science people, when we model our machine learning algorithms, it is always the case that the data will be inputted in number form. It's not in any other form. It may be audio, video, image, text, and all those things that many of you may be aware. So the goal is to transform this complex alphabet collection, which is a genome sequence, must be converted into the number form without any loss of information features within a particular genome or protein sequence. Next, please. Now, there is one more terminology used, that is SNP sequences. So when we call genome sequences, normally the protein, DNA, RNA, these are the common words which every human being is aware of. Like the people who are from sciences, engineering, and any other domain, they heard about these terms, proteins, RNA, and DNA. Here, there is one more term, SNP, and you can quickly understand it. Whatever sequences you can see here, 3 different sequences, violet, blue, and another one is yellowish one. So how these amino acids are varying, that means the series of alphabets are varying. And whenever there is a change, for example, you look at that inclusive rectangle, that is highlighted as SNP, that is single nucleotide polymorphism. It's a bioinformatics terminology. So how, whenever these amino acids are changing, like if it is occurring A, then it is changing to G or T. Whenever such changes are occurring, we used to say that these sequences are termed as SNPs. And there's a lot of study involved for the bioinformatics people here to identify such changes in the amino acids or these nucleotides, right? And that's why there are a lot of infinite number of problems available with variety of plants, variety of genomes related to human genomes or any living thing, identifying such SNPs that when it is changing. Because if it is changed, that means certain kind of behavior gets changed, right? So obviously, whenever we want to observe something, I am taking here the example of plant. So in plant, what we are going to observe or what kind of expectations from us, from the soybean scientists. So for example, some soybean plant, and we are talking about SNP sequences of those soybean plant. So we want to identify these changes because we want to recognize whether plant is getting infected or not, so that we can identify the disease with which that plant is suffering. And then the soybean scientists can identify quickly that this is the way, the proactive action we can take, and we can procure the crop, right? So as Dr. Ratnapalki already mentioned you about how important soybean crop is, and India is the 4th producer in the world, and the revenue gets increased so much if soybean production will be very much. So it after all, it affects the revenue of the government, right? So working with these soybean crops mean identifying the disease diagnosis is one target. That's a machine learning problem because you are predicting something from this data, right? Another thing is try to identify that how much temperature is to be required, whether it is drought resistance or not. So there are so many aspects which we need to identify from the available set of crops or plants with which this data gets generated. And we used to take this data in our machine learning algorithms and try to perform lots of such predictions for the disease diagnosis, for maintaining a particular temperature, humidity, and maybe it is drought resistant or on other kinds of analysis, right? That obviously we alone cannot do. And the domain experts like Dr. Ratnapalki is the domain expert who is helping us to understand this data. So for us, the computer science perspective, we guys are worried about the data, what data we are working. And if you look at these genome sequences, these are very complicated data. It's not, you're looking in the slide here only 5-10 characters, but it's a huge set of characters in a single sequence. And there are so many such sequences keeps on generated regularly. So if you look at a particular soybean plant species, there's maybe lakhs of sequences keeps on generating, right? And nowadays, if we talk about the online data, we must assume the data keep on generating. It's not offline data nowadays. So, if we look at the research aspect in the machine learning algorithm, now it is switching to the online machine learning algorithm. So right now, I'm just talking about the scalable machine learning algorithm, that how the learning will happen in parallel manner. On the different multiple machines, we are able to execute or perform learning over these genome sequences, which is complicated one. So let us quickly look at the complexity of this data with which the computer scientists are very careful to analyze it so that it will not lose the information by interacting with the bioinformatics scientists. So like SNP is one of the form of the protein data sets. In fact, it is available for RNA and DNA as well. Next, please. So, let us go ahead because time is not very much. Quickly go ahead with what is about the data. So look at some slides like whatever I discussed till now. I am hoping that you are able to imagine this colorful alphabets are representing the protein sequences. One of the examples shot of it. So you can see that there are a number of such sequences are available, and there is no limit. And there are tools available, like BLASTP is one of the tool available through which, if you go back to the previous slide, please. So this previous slide, actually, if you look at concentrate on one sequence of protein, here the sequence, all the sequences are aligned. That means the length of every sequence is equal. But when we collect the raw form of the data, it's not aligned. If you go through the next to next, which is unaligned sequence. So this is the raw form of the protein sequences, which are actually coming in raw form. And what is complexity involved here, the challenge involved here for the computer scientists is, if you look at line number 1, 2, 3, 4, and number of rows, there are so many alphabets you can see. So, and there are some dashes available. These dashes are called as gaps. Obviously, these gaps are not carrying any meaning. Whenever these alphabets are occurring, that means some nucleotide is occurring or amino acid is occurring. So that are of interest. So first of all, we have to make the alignment. Removal of the gaps is one of the things. Remove all the gaps, make all the sequences aligned. And then when it is aligned, obviously they are all characters. And for applying on the machine learning algorithm, we have to transform that character version of the sequences into the number form. But we must take care of that. Whatever we are doing, we should not lose the feature of any protein sequence which is generated. If we are losing the feature, that means we are losing the traits or characteristic of that particular plant. And we, whatever decision making task we are doing, whatever predictions we are doing, that is wrong. So that we must be very much careful for this data analytics part of the genome sequences. So that is what we are handling in the funded projects. Please. So for this, this we are parallelly doing. We are developing machine learning algorithms, the scalable machine learning algorithms, which we used to say fuzzy clustering algorithm, because this problem is a clustering problem. If we go in deep of the genome sequences with the previous slide, and only the alphabetical sequences or the protein sequences are visible to you, or the SNP sequences are visible to you, they are not labeled, right? And based on their similarity, we are going to cluster them. So, this is obviously a clustering problem, and the people who are from computer science, they are knowing what is about clustering. However, some preliminary slides are there to quickly understand the clustering. So whatever problem we are working with, it's a clustering problem of protein sequences, SNP sequences, and we developed the methodologies for transforming our data pre-processing of these protein sequences, as well as you can see on this slide, we developed the scalable SNP feature extraction technique. If we added the word scalable, that means, as Dr. Ashish mentioned, that parallel computing is definitely required to handle huge data to improve the performance. And nowadays, resources are available with us. So we did the same job. We developed our feature extraction techniques, and whatever computations are involved in that feature extraction technique, we are doing that computation in parallel manner. And that's why we have added the word scalable. So you can look at the references here, paper number 1 and 2 in the footer. So these papers we referred, and in fact, in paper number 2, we published that methodology. And in paper number 1, we have taken the aspects of how clustering has been done for DNA sequences. So that we have incorporated in our case, and we developed a methodology which reduced a single protein sequences into the 12 dimensional feature. So in that way, all sequences are transformed into the 12 features only. So that was the reduction after designing this methodology. So paper number 2 is our methodology that is published in Elsevier journal. And we have implemented this methodology in Apache Spark, which is well-known framework for doing parallel computation. Right. So next, please. So you can quickly look at that method. In this method, we evaluated only parameters. First is the total distance. Another one is the variance of the distance. And one more is the length. Okay. So for because if you look at the SNP, it is represented by ATGC, 4 characters. So in bioinformatics term, we call these ATGC as nucleotides, right? For computer science people, they are alphabet because we are worrying about how to transform alphabet into the number form. So these, what is our goal? Whatever sequence you will see the sequence which are collection of multiple A's, multiple T's, multiple C, and multiple G's. Only 4 characters which are collected anyways and forming a particular protein sequence. But after all, everything will be converted into number form. Before conversion into number form, we are reducing it to the lesser amount so that the transformation will be much easier. And that is what the reduction we have done with this methodology by computing only 4 parameters: total distance, the variance of the distance, and that way the feature vector is formed like this. Okay. So if you look at the last line, Neha, previous slide, please. I want to explain them. You look at slide number 13, the last line inside the bracket. So L subscript A is one parameter, then tau subscript A, and then D subscript A. So that means for every nucleotide, A is a nucleotide, right? So for every nucleotide, there are 3 parameters. For T, again, there are 3 parameters. For G, again, 3 parameters, and C, again, 3 parameters. So that way, the 12 parameters are there. So what, it may be any sequence of ATGCs in a particular SNP. After all, everything is converted into this 3 parameters for each, hence it is a 12-dimensional pattern. Okay, next, please. So look at this diagram. This diagram is a flow chart which shows the data pre-processing involved, which we are doing on the Apache Spark setup with this reduction in SNP sequences, which is a scalable one, scalable pre-processing methodology, which we have developed for the soybean data, the data collected from Soybean Research Center, and still we are using it in innovations. After pre-processing, we applied on the developed scalable clustering algorithm. So you can see here the term KSLFCM. This is our methodology, utilized version of scalable fuzzy clustering C-means algorithm. So this flowchart is showing the whole picture that how pre-processing methodology is combined with the scalable fuzzy clustering algorithm, right? So what I want to share as a computer science person is that we guys are not only responsible to just design the scalable machine learning algorithm, we should look at the data part as well. For whatever data we are working with, we should work on the data pre-processing part as well. And genome is such an area where, you know, infinite number of problems are available, and you must go through the deeper details of it for the proper understanding so that you can design the novel techniques to do the previous or pre-feature extraction and reduction. Hence, you can improve the performance of your scalable machine learning methodologies as well. Next, please. So this flowchart is giving you the more detailed view of this novel SNP feature extraction methodology on the left-hand side. The right-hand side, the dotted rectangle is enclosing the steps of the fuzzy clustering algorithm, which will be explained by my colleague, Dr. Neha Bharil, in detail. At least one algorithm. We developed multiple algorithms want to share with you, Dr. Neha Bharil already awarded the degree, PhD degree in the scalable machine learning algorithm. She developed methodologies which are general one, not specific to any genome sequence, which is applicable to any kind of data. Dealing with data is another part. Developing scalable machine learning algorithm, that is another part, and that is the area of research for computer scientists. So next, please. So look at, now this is one of the example to quickly understand SNP, whatever I discussed with you, that there are 5 sequences visible to you, which are numbered 1 to 9. That means 9 alphabets are there. So for bioinformatics people, it's not alphabet, they are nucleotides. But for computer science people, it is alphabet, because we are worrying about to transform it to machine version, that is number form. So you can see everywhere in every sequence, it is ATGC only and their occurrences. So based on their occurrences, we have computed 3 parameters, that length, then D, then variance. So three parameters for A, T, G, and C, and hence uh, every sequence is converted into the 12-dimensional feature vector. Okay, so that means if you look at any kind of sequence of data is coming, it is reduced to the 12 features. So that way, if you look at the number of columns of your data, it is reduced to the 12 columns only. And if data is unlimited, it's a huge reduction if you say it's a big data. Next, please. So I hope this time you're able to understood. I've taken many examples, and in fact, you have seen these sequences, and you can realize that why this genome sequence analysis problem is a clustering problem, because it's not labeled. And obviously, we need some unsupervised learning algorithm. Just based on looking at the similarity of one sequence with the other sequence, we try to group the similar sequences all together, right? And then we say we are going to go ahead with the clustering. So I'm hoping that maximum people are aware of the clustering, but few slides we have added intentionally. So next slide, please. So next, these are few basics with unsupervised. If data is not labeled, simply we, based on some similarity principle, first sample is compared with the other one. If they are similar some way, then we will group them together, and hence we call it as a clustering. But why fuzzy clustering? Because we are applying the fuzzy concept in the clustering. Now, why fuzzy? Because we know that whatever real data is coming, some features may be common, and the samples or the SNP sequences which are occurring may get overlapped. If you look at all data distribution in real life scenario, the data distribution get overlapped, and this overlapping thing will be resolved with the help of applying fuzzy concept, right? So fuzzy is a different area in soft computing, which needs to be discussed separately, but you can quickly understand here that how this fuzzy aspect is involved in the clustering scenario to handle the overlapping of this sample distribution. So next, please. Now look at this diagram. You look at this overlap region. One circle is overlapping with the other one. Overlap region means the patterns or the samples which are fuzzy may be belonging to, say, class C1 or class C2. Say circle 1 is C1 and circle 2 will be C2. So such a sample, which are confusing sample, we have to handle that thing with the help of fuzzy. Now in fuzzy situation, we always work with the computation of membership degree. Okay. So in CRISP case, we just say that some sample belonging to C1 or C2. And this way we work in CRISP clustering. But if we say fuzzy, then there is always a parameter which we have, that is the membership degree computation. So for every data point or for every SNP sequence, right, we associate a membership degree. So if you go ahead with the fuzzy principles, fuzzy logic theory, which is a computer science theory people normally applied in machine learning scenario, it is always the case that for every data point, you have to compute a membership degree. That just gives the degree of belongingness of the sample which is lying within the overlapped region, right? So only for the overlapped region, in fact, for all the samples, and the overlapping samples are going to be recognized with the help of the membership degree computation. That means how much it is belonging to, say, C1 or C2. If say degree of belongingness of some sample, and it is always lie between 0 and 1. If I say sample P1 is belonging to, say, C1 with, say, 0.2, and second sample P2 is belonging to same sample C1 with say 0.8. So P1, P2 both are having some membership degree value. P1 is having 0.2, P2 is having 0.8. Now, which one is having more belongingness? Obviously, 0.8 is greater than 0.2. That means point P2 is more closer that particular class or area for which you are looking or deciding that this sample is belonging to this thing. And that's how the membership degree computation helps us to handle this overlap samples, and we can apply fuzzy logic in that way. So based on this fuzzy clustering algorithm, FCM algorithm, which is very common in basic algorithm in clustering domain, and in 90s, in fact, very early days, it was designed when this fuzzy logic theory was introduced by the Lotif Jade in 1968. Just after that, the machine learning guys have designed this FCM algorithm. And what they did that for every sample, they computed two parameters. Because it's a clustering algorithm, obviously, first computation you have to do is the cluster center computation. And whatever cluster center you decided, say 3 cluster center computation, that means whatever samples are coming, say SNP sequences are coming, they get clustered around all these 3 clusters, right? So what computation is involved here? Cluster center computation, right? And another is the membership degree computation. So look at the equation number 2, that is the membership degree computation. What is membership degree computation? That whenever any sample is coming, we check whether it is with closer to the cluster 1 or cluster 2 or cluster 3, because you have decided 3 clusters. So checking with the sample is closer to which one. For that, we compute this membership degree, that is Uij, if you look at this equation number 2. So first computation involved is the membership degree computation. And previous slide, please. And another important computation is the cluster center computation, that is equation number 4. Okay. So whenever sample, say if sample is closer to say cluster number 3, depending on whatever membership degree you are computing, whatever membership degree computation is highest to that particular cluster that sample is belonging, and then we expand that cluster by updating its cluster center value. That means we are keeping that sample within that cluster, and that way we are updating this VJ, that is the cluster center. So what is the basic concept here is computing two things: membership degree computation, degree of belongingness of every sample, and the cluster center computation, updating a particular cluster whenever you this particular sample is belonging to this cluster, and that way the clustering is happening, and it keeps on clustering a particular cluster. Now these two computations being done in parallel manner whenever we are going to design scalable fuzzy clustering algorithm. So that is what we have analyzed, that how we can do the computation of membership degree with respect to every sample in parallel manner, and how we can make the cluster center computation in parallel manner. Because there are 3 cluster centers with which you are computing the membership degree with all the samples. If there are n samples, with all the samples with respect to C1, C2, and C3, 3 clusters. For second sample also C1, C2, C3. That means this task can be done in parallel manner. And obviously that is helpful to go ahead the distribution of our task and able to help design that scalable fuzzy clustering algorithm. So next I am stopping here. Now Dr. Neha Bharil will be highlighting on the scalable fuzzy clustering algorithm which we designed and how we are applying on the genome data that will also be shared. Thank you. If any question, I will be available and will reply at the end.
Hope Dr. Tiwari, am I audible to everyone?
Yeah, you are audible.
So as Dr. Tiwari discussed, that we have identified the equations and the parts in the fuzzy clustering algorithm which could be executed in parallel manner based on identification. We have
Neha, your voice is cracking. For others also it is cracking.
Now I am audible.
Audible.
Okay.
Switch off your video, I
Off your
guess.
video.
Yeah, just a minute.
Please switch off your video so it will be better.
So now I am audible to everyone.
Yes, yes.
So the very first algorithm which we developed is the scalable random sampling with iterative optimization fuzzy C-means algorithm. So as Dr. Tiwari discussed, in this algorithm of the fuzzy clustering, we identified that calculation of the membership degree, specifically the calculation of distance of every data point from a cluster center, is basically independent of computation of the other sample distance to the cluster center. So based on this identification, we have designed the scalable clustering algorithms where this calculation be executed in parallel manner. Okay, but this scalable random sampling with iterative optimization algorithm exactly making use of the literal fuzzy C-means algorithm, that is this algorithm. So first we have to make this algorithm in parallel, and based on this we have made the few changes in the scalable random sampling algorithm. And then we identified that there are the few, you can say, shortcomings of the scalable random sampling algorithm. So based on that, we designed a kernelized scalable random sampling algorithm. Kernelized scalable random sampling algorithm, the motivation behind designing this algorithm is when we have the non-linear distribution of the data. Okay, for such kind of the non-linear distribution of the data, the scalable random sampling fuzzy clustering algorithm may not work. Okay, so we need to project the data into the higher dimensional space so that we can identify that how are the separable clusters we can assign to our data points. Okay, so based on that, we have in this also kernelized scalable random sampling algorithm, we make use of the scalable literal sampling algorithm because the concept behind them, that is same. Only thing is that the distance function present over here has been changed in the context of the kernelized clusters. We have made use of the RBF kernel over here. So based on these algorithms, we have the few publications. So you can see corresponding to SRS IO FCM algorithm, we have a one publication get published in IEEE Transactions on Big Data in 2016. And we have another publication based on the scalable kernelized fuzzy clustering algorithm. This is also get published into the another transactions, that is IEEE Transaction on Emerging Topics in Computational Intelligence. So how we developed these algorithms, as both the algorithms are based on the basic idea that you have to make the literal fuzzy C-means algorithm scalable. So if I go back and discuss here, as I discussed, that this distance computations can be executed in parallel manner. So if I execute this into the Apache Spark framework, I need to identify that which calculations could be executed in parallel. So that becomes my mapper functions. So if you come here, we have execute that membership in parallel, and corresponding to each distance calculations, we will be having the multiple mapper functions executed. So these mapper functions are executed parallel onto the multiple machines. Now, this is resource management unit is there in the Apache Spark cluster, that is YARN, which basically responsible of distributing the work onto the multiple nodes attached into our cluster. And once the execution of multiple mapper functions being done, on the backend side, shuffling will happen, which will be nothing but a sorting and arrangement of this data. So once shuffling is happened, the reducer will be collecting the job execution done onto the mapper multiple functions, and then reducer will able to give the accumulated result to the main master machine. Okay, so based on this, the computations which is shown here in the equation 2 has been executed in parallel manner in this algorithm. And then we identified that there are the possibilities of optimizing the space, okay, and storage spaces specifically. One of the major motivation of using the Apache Spark in the context of the Hadoop here is that we designed the scalable algorithm and executed on the Hadoop MapReduce. But we later identified that working on a huge GBs of the data, Hadoop used to take a significantly higher time. And when we executed that same thing onto the Apache Spark cluster, this comparatively resolves the issue and executed 100 times more faster than the Hadoop MapReduce. But in the executing into the Apache Spark, which works on the in-memory computation, resolve the problem of execution, working in a faster manner. But there is still the possibility of optimizing the computation and reducing out the space. So we identified that computing the third step, okay, that is fourth step, sorry, the computing the cluster center calculation, we cannot execute this into the parallel manner because cluster center execution depend on computation of UIG corresponding to all the data points. So what we did it, rather than saving individually the numerator and denominator, we accumulated as is the result and saved it into the memory. Okay, we computed this numerator and denominator computations we have been saved into the some distance. So by doing this step also, we saved a significant amount of the time and done the execution in the faster manner. And rest all these steps are similar to what is there in the basic fuzzy C-means algorithm. Now, based on this algorithm has been inherently be called into the scalable random sampling algorithm. So how random sampling algorithm works? Suppose you have 100 GB of protein data collected from any bioinformatics research center or from the NCBI. For 100 GB of the data, because your standalone machine is unable to execute and work on 100 GB of the data, what you did it, you have been connected multiple systems into the Apache Spark cluster. And because you are working onto a Apache Spark cluster and there are the mapper and reducer programs you have, you can divide this data into the various chunks. Suppose I created a chunks because I know my individual machine is capable to handle 10 GB of the data based on my computations, machines connected in a cluster. So each machine can able to handle 10 GB of data. So I have created 10 chunks of that data, and all these 10 chunks will be processed in a parallel manner onto the each machine. Now, one chunk which is processing into the one machine, the computation of the cluster centers, the computation of the membership degree, that is this has been executed into the multiple parallel manner also, because within a one machine I will be having the multiple cores. So I'm utilizing multiple cores like that. Okay, and within that machines, the results are being computed in parallel. Like that, I have a 10 machines to be connected in a cluster. So all these computations could be done in a parallel manner rather than the sequential literal fuzzy C-means cluster. So this way, I am making use of scalable fuzzy, literal fuzzy C-means clustering and doing my execution work in parallel, which is going to give me the cluster center and the membership degree. Based on that, I have to compute the updated cluster center. Okay, so this updated cluster center computations could also be done onto the parallelly onto the multiple machines, because after sorting, the data is being supplied by the reduce function onto the master machine, and the master machine is responsible for dividing the jobs again in the execution in parallel manner through the yarn management unit. So based on that, this is how the computations are done. But we identified later on that there are the certain drawbacks in the scalable random fuzzy C-means algorithm. Is that one is that for working with any fuzzy clustering algorithm, you have to decide how many clusters would be initially be given to the algorithm for clustering the data, as well as what is the initial cluster centroid going to be. So what we are pre-assuming is that corresponding to one subset, we are taking few data points as a center for the initialization of the cluster centroid and passing the final cluster centroid of the first subset to for the clustering of the second subset as a basic initial cluster center. But we identified what will happen because you are dividing these chunks randomly. It might possibility, because we don't have a labels associated with that data, but actually might be the data belongs to a similar class, might be possibility that data sample of the one class would be given in a one chunk of the data, and we don't have a equally distributed data with us while creating a chunk. Then this creates a problem because the first subset will only have a class 1 sample. In that case, the centroid passed as a base center for the clustering of the second, you can say, a subset will create a huge issue of divergence. Okay, that would be biased result you will get it from the second subset clustering. So based on that, we modified this thing and we worked on merging the membership matrices results obtained from clustering of the two subsets. And another thing is that we identified is that use of the kernel function would give us more result when working with a more diversified data points, okay, where we don't have actually linearly separable data. So for such kind of the data, we make use of the radial basis kernel function. Okay, so this is how the modifications we have done in the base fuzzy clustering algorithm. If you look, the base fuzzy clustering algorithm is based on the Euclidean distance evaluation. Here, rather than Euclidean distance function evaluation, we made use of the RDF kernel function. So this is how the RDF kernel function has been introduced, and this is the definition of that RDF kernel function. This will project the data into the higher dimensional space so that we can able to see how the data points can be grouped into the separable clusters up to an extent. Okay. So again, the concept remains same. We make use of the RBF kernel function in the literal fuzzy sequence algorithm and made it scalable. So this time we are making use of the SLFCM. Okay, only thing is that the definition of the Euclidean distance kernel functions get changed in this algorithm. And again, the execution in terms of mapper and reducer work will remain same. And based on that, we designed the KSRS IOFCM. In this, we are making sure that it does not happen that the first subset cluster center, which we received as a final center, will be used directly as a base center for the clustering of the second subset. Instead, first we cluster first subset and acquired its cluster center, and then we cluster second subset. And based on the cluster center received from the first subset and second subset, we merge both these centers and compute the combined membership matrix. And that should be feeded for the clustering of the third subset. So that will resolve the problem of biasness as well. So this is how the flowchart of the entire KSRS IOFCM algorithm is. We have a data set, like I told you, 100 GB of the genome data we have. We divided it into various subsets or the chunks, that is 10 GB, and being supplied in parallel onto the multiple machines. So what is the important part here in the Apache Spark is that you don't have to do the computation by sending the data to the master machine which holds the algorithm. Rather than the algorithm or the computation part will be sent to the slave machine where the data resides. So swapping of the data saves lots of the time here, and everything is done in the in-memory computation. So that resolves the time consuming sequential fuzzy sequence algorithm, the problem which occurs over there. Okay, so the computations are being sent, or the algorithms are to be sent to the slave nodes, and once the computations are done on all the slave nodes, the results are being accumulated and given to the master machine. And all these, how these machines are interconnected, being taken care by the yarn management resource manager, that is yarn, yet another resource managers, you can say. So coming towards addressing the data problem, we worked on protein data, and like we developed a feature extraction approach for the SNP, we also developed a scalable feature extraction for the protein data. So while developing a scalable feature extraction for the protein data, we have to make sure that the basic data which we have, we should lose any information out of that data. So we perform various alignments onto the protein data, and after performing the alignment, we want to extract the feature. So while extracting the feature, the two very important concepts in the context of the extracting features from the protein data is the local similarity and the global similarity. So local similarity is how a amino acid changes its position with respect to number of sequences present within a superfamily. So in general, if I talk about how a particular amino acid A change in every sequence column wise. Similarly, if I talk about the local similarity, that within a sequence row wise, how many times a amino acid changes position. Suppose amino acid A present at first position, within that sequence, how many times amino acid A present at multiple positions within that sequence. So if you take into account this local and global similarity, you taken into account all the perspective of the variations occurs within an amino acid. So based on these two concepts, we designed a scalable, you can say a feature extraction approach, okay, which extracts 6 features. And these 6 features has been taken into the consideration based on the famous study given by the scientist Palm, based on the exchange group, because he has given 6 exchange group. As we already know, the protein sequence consists of 20 amino acids. So he has given, based on structure similarity, that certain amino acids, or out of these 20 amino acids, with each other on the basis of their structure, so they can be grouped into particular exchange group. Like that, he divided 20 amino acids into 6 exchange groups. So based on that assumption, we computed a local and the global similarity, and we identified that each sequence, which can be of any length, we will only get 6 features out of that corresponding to it. So based on that, we have designed a scalable feature extraction approach. So in the first approach, we encoded these protein sequences in terms of exchange group. And in the second stage, we compute the global similarity. And in the third stage, we compute the local similarity. And we did this computation in parallel manner. And based on that, we designed a 6-dimensional scalable feature extraction approach. So this scalable feature extraction approach has been designed on the basis of one of our publication we have done in another journal, that is Procedure Computer Science, where we only designed a sequential feature extraction approach, and later on we analyzed that there is a need when you are dealing with the petabytes and exascale level of the data. So this is how the flowchart of the entire scalable fuzzy clustering algorithm, scalable fuzzy clustering algorithm, as well as scalable feature extraction approach. So you feed a protein data, and then you perform these 3 stages job in parallel manner. Okay, so this exchange mapping into the exchange groups could be done into the multiple machine in a parallel manner using a mapper function. Similarly, computation of the global similarity and the global similarity corresponding to a sequence, these steps could not be parallelized because we have to feed all the sequences at once, but a local similarity measure could be making in parallel. So again, a mapper function has been introduced over here for doing the computation in parallel, and the accumulated results will be sent to the master machine by a reduced by key operation, which is a 6-dimensional numerical feature. Once we extracted the 6-dimensional feature vector corresponding to how long the sequence is and how much is the size of the data is, we feed this feature, extracted feature, into a scalable feature extraction approach, which is also executing in a parallel manner, as I discussed already. Okay, so once we identify the cluster centers and the membership information, we have to evaluate the result based on validity measures. So we have many validity measures being designed by the scientists, but basically in the context of genome clustering, these are the most widely used validity measure, that is the Lotte index and the Davis-Baldwin index. So we have evaluated these index to judge that how efficiently our 6-dimensional feature extraction approach is working and how better our scalable fuzzy clustering algorithm is. So this is how the setup we have done. We have an Intel Core TM machine with us, which has 16 GB RAM, 1 TB storage, and each master machine will have 32 GB RAM. Like that, we have a cluster connected, all the nodes connected in our clusters, and we have designed all our algorithms in the Python and use Apache Spark cluster setup 2.4.0. So we have collected some of the data from the NCBI and some of the data from Soybean Research Center from Dr. Milind Ratan Bharti, and we have evaluated the results on these indexes, as I discussed with you. So there are certain analyses which we have projected here for various algorithms. You can see over here, like we developed KSRS IOFCM, KSLFCM algorithm, SRS IOFCM, and SLFCM. You can see here, this color division shows that we have a 2 variety of the plants, that is wild and cultivated. So actually these are terms as the 2 different classes. So if wilds category of the plant genome should not be grouped into the cultivated one. So if you see here in the context of the SLFCM, you can see here wild and cultivated group for major of the classes are overlapping with each other. Whereas in case of the SRSIO, this issue resolved up to an extent, but in case of KSRSIO FCM, this has widely been resolved. If you see here, this green color is for the cultivated. Okay, this only green color is overlapping with the white, but rest, if you see, the violet color is not overlapping, corresponding to the cultivated with the white. So we can see in case of the 5 number of the clusters and the 10 number of the cluster, KSRS IOFCM applicability in terms of the efficiency is much more better as compared to the other designed algorithm. So we have improved this work over the period of time. First, we designed a scalable random sampling approach. Later on, we analyzed that for some certain kind of the data which are non-linear, we have to move towards the kernelized version of that algorithm. So we have identified here the efficacy of the KSRS-IO algorithm by evaluating on this data. So again, we have projected some of our results on the protein data sets over here. So these are, you can see over here, I have not projected another scalable approach which we have developed, but I have discussed here the 6-dimensional feature extraction approach. This is a kind of the results we are getting it up over here in terms of the DBI and the slotted index. So you can see that the proposed approaches work well as compared to the other approaches in terms of getting the lower value of these indexes. So this is again for the another indexes, that is DBI. Okay, so the higher value of the DBI will denote a better clustering results we are achieving it of, and that is what you can see it over here as compared to the 60-dimensional feature extraction. So this is the publication which we got it corresponding to the scalable kernelized fuzzy clustering algorithms we have applied onto the SNP dataset, which we have collected it from the ICAR ISSR Indore. So now we analyze the significance of developing these approaches and applying it onto the genome data to detect genetic risk factors for complex plant disease by identifying disease associated SNPs. Okay, because we are identifying that during the clustering that which particular SNPs are being affected by a particular diseases. And as Dr. Tiwari mentioned, that SNP clustering is also required to identify some of the genes, genome sequences, which can be resistant for the drought or the heat, or may not be resistant for the drought and heat. So thus, this identifications can be done using the clustering technique. Identification of the key related genes associated with higher quality, oil quality and quantity. So that is what our major motivation behind applying these scalable clustering algorithms onto these genomics data. So these are some fund research projects. We got it in as Dr. Tiwari being a PI of these projects, and we as a collaborator. So one project has already been successfully completed in the year 2020, which has been given by the agency CSIR. And another project we recently got it from the CSIR. Okay, and this is ongoing project right now. And the another project we get it from the NSM supercomputing mission, under which we are organizing this workshop also. This is a 2-year project and we are working on this project. The motivation in this project is right now we made use of the CPUs only for designing a scalable clustering algorithm. As Dr. Arya suggested, that we can have a synchronization between making these algorithms scalable further by making a synchronization between the CPU and the GPU. So now our advancement towards is designing a GPU-based algorithms and making for some of the further innovations in the scalable clustering algorithms. And there are the few research publications we have that out of all the works we are doing in this domain. With this, I would like to rest my talk here. I would like to take the questions.
Yeah, thank you very much, Dr. Neha Bharil and Dr. Tiwari for excellent presentation and explaining in detail about clustering algorithm for SNP and proteins. So there are several questions. Dr.
Yeah,
Tiwari.
yeah. So there are few questions. First question is from Hamza Ramzan. Why we go for multiple sequence alignment? What will be the basic benefit of this? So I think he's asking for that protein alignment, sequence alignment.
Yeah.
So as I mentioned, yeah, you are answering, Neha?
No problem, ma'am, you can.
Yeah. So Hamza, your question is very nice, but looking at that question, I feel you are not from computer science background. So as I told you that in machine learning algorithms, whatever inputs we are giving, it can be number, character, picture, video, anything. Everything must be converted into number form because computer is a number processing system. Okay. So here, if we say genome, it's a collection of alphabets. Okay. And in raw form, as you have seen one of the slide I was showing that at random, these ATGC sequences are generated, the protein sequences are generated. So why we are aligning? So that every sequence is of same length. You look at this, every sequence is of same length. If say sequence is 128 length, then the second sequence will also become 128 length. So this is raw form. The slide which is visible to it is raw form, which is unaligned. That means maybe first sequence may be a 50 characters, second sequence may be 300 characters, third sequence may be 1000 characters. But when we apply to the machine learning algorithm, input length must be same for all the samples. Okay. We cannot do the variation in the inputs which you are applying to the machine learning algorithm. So to make your inputs compatible to the machine learning algorithm, we have to pre-process this data. And very first task is to remove the gaps and make the sequences aligned, mean of same length. Okay. I hope you are satisfied with this answer. Next is from Mitali Rai. How does data clustering help solving challenges of data mining? Right. So data mining and data, it's not the discussion on data mining and machine learning, but obviously when we say data mining means we are discovering some hidden information from the available data. And that means when we apply machine learning algorithm in certain application, then we say we are doing some data mining. So here, obviously, when we apply to the problem, this genome problem with the machine learning algorithm, obviously we are doing some data mining. But for answering this question, I want to take some real life example. For example, you are buying several mangoes from the market, hapus, langda, totapari. There are variety of mangoes, and you purchase say 5 varieties of mango, and in one bucket you have to keep on putting all the mangoes. When you come to home, what's the way you are going to manage all those mangoes? You collect the similar kind of mangoes all together, right? Now, in on machine also, because what you are doing in machine, what do you want with clustering? You want to make the machine intelligent the way human being works. Okay. Now here, because you have your knowledge that this mango is different from totapari, or this mango patasa is different from langda, right? And looking at their features, you can separate out and group the similar kind of mangoes all together. Okay. So this you are knowing. With your knowledge, you are grouping them all together. If someone is available to teach that thing, and based on that, you are doing that grouping, that's a classification. But if that is not available, that someone is telling you, and without the knowledge of anything, if you are grouping something, that means based on some similarity, similar characteristics of the objects, you are grouping them all together, right? And you are not knowing that what is this thing, but just looking at external features, you are grouping the similar kind of objects all together, and that is called clustering. So in machine learning scenario, when we look at the types of machine learning algorithm, there are supervised algorithms, unsupervised algorithms. Supervised, samples are labeled, that means some guideliner is available. Unsupervised mean there is no guideliner available, data is unlabeled. So these protein sequences which keeps on coming, it is not available that this protein sequence is showing the infected one, or this protein sequence is the plant, or something like that. Because everywhere these nucleotides or amino acids keep on changing. So we don't know which sequence is giving which quality of the plant. That is not labeled. If it is not labeled, then clustering is applied to just look at the similarity between first sequence with the second, third, and so on. And that way the clustering will happen in iterative manner. Right? So that way the data clustering obviously helpful to handle the challenges of data mining when samples are unlabeled. This is the kind of problem which we handle in data mining. In fact, broadly, if you look at data mining paradigm, there are 4 varieties of problem: classification, clustering, association, right, and prediction. These are the 4 broad varieties of problem that are handled. So clustering is a kind of problem we are handling here, right? So next, Neha, please you answer this. It is related to KSRSIO FCM.
Okay,
Are
so
you
the
able
next
to see,
question.
Neha, this question?
Yes. Am I audible, ma'am?
Yes, audible.
Yes. The next question is, do we have an outcome of experiment comparison metrics on various big data to show the effectiveness of one algorithm, that is KSRSIO FCM, in comparison with other algorithm? So I would like to answer this. If you see this publication, the very first publications we have in this domain, SRSIO FCM, Its comparison is given in this paper on various performance metrics, like for an example, usually to evaluate the quality of how good your clustering algorithm is working, we have NMI measure, F measure. So on these performance matrices, parameters, we have populated the result in this paper. And apart from that, on the context of scalability, if you talk about in scale up factors, we have also populated the result in this paper. And after advancing this algorithm and developing the KSRS-IO FCM, we have published this paper. And in this paper, again, the comparison of KSRS-IO FCM in comparison with all our previous work and earlier existing clustering algorithm has also been populated on the same factors. So I think you can view this papers and you can able to see the comparison metrics, how efficiently the proposed algorithm is working in context with other algorithms.
So I hope we
So I
answered
hope-
the query, and yeah, for more interaction, you can drop your email. You can be in touch with all the organizers.
Okay, so if there are no
Okay.
other questions, I'd like to thank Dr. Aruna Tiwari and Dr. Neha Baril for the excellent presentation. And this was very
Welcome.
useful, and so to all the participants. So thank you very much. Thank you all. And we
Thank
will
you.
join in the next session at 2 p.m.
2 o'clock.
Yeah, 2
Yeah,
o'clock.
2 o'clock.
Yeah.
Thank you, Dr.
Thank you.
Ratnavati.
Thank you.
Thank you.
Thank you, ma'am. Thank you, sir.
Implementation, such kind of things, comments. Yes.
Welcome back, everyone. Now I would like to welcome our new speaker, Mr. Amit Saxena, sir. Welcome, sir.
Thank
Now
you.
I would like Dr. Om Prakash, sir, to please give a brief intro about Amit Saxena, sir. Thank you, sir.
Thank you, Nilesh. Am I audible, Nilesh?
Yes, sir.
Welcome, Amit sir. So till now in the whole workshop, we have listened about the high performance computing, and the several speakers told about that we required several processors, or this is possible only through several processor to compute such big data, especially related to our agriculture. But is it possible to compute such big data in only one system? Yeah, this is interesting, and it is possible. So this is possible only using quantum computers. So how quantum computer work, how it can be useful for processing such big data, or high performance, can produce high performance computing. I would like to introduce Dr. Amit sir. He will so Amit sir is Program Director of Quantum Computer Development in CDEC. With more than a decade of experience, he has played an important role in many strategic and collaborative projects under Government of India. He is playing a major role as an expert member in the implementation of National Supercomputing Mission projects. He is also working as a member of Task Force for Big Data in Life Sciences, appointed by Principal Scientific Advisor, Government of India. Since last 3 years, he has taken the new task for development and implementation of quantum algorithm in scientific area of research. He is working for the development of HPC-based quantum simulator for implementation and testing of quantum algorithms. He has also organized various quantum computing training and workshop under the CDEC flagship. He is also playing a key role under the National Mission of Quantum Technology and Application and as a CDEC representative. Sir, I would like to welcome you. Please enlighten us with your knowledge with this interesting topic. Welcome, sir.
Thank you, Dr. Om Prakash. So, are my slides visible?
Yes, sir.
Yes.
Yeah. So, is it changing? Moore's law is.
As of now, you are on slide number 2.
Yes, sir. Okay. So,
yes, sir.
yeah.
It's
So I
changing.
think that's great. I think all the system is working, and I think we have to depend on internet. And soon we will be having quantum internet. So I hope that this type of glitches will not happen, and we will be having virtually close. And so yesterday I was attending one panel with Russian. So they were having all the speakers virtually at a distance, and then it was appearing as if they were together. So I think since technology is growing very fast, so soon we will be having similar technologies, and which will enable us to interact. And the beauty about this technology is that you can see a lot of more than 2,000 students, they are listening to us and on the live platform. And without this technology, it could not have been possible. And I think if you do a physical gathering, then you can have limited people. Now, I think we are very thankful, I think, to IIT Indore that they are organizing this, and we are also associated with them. And but I think a lot of work has been done to enable this. Since last 2 days, we are really listening to very interesting talks, and a lot of things we have heard about genomics. We have heard about HPC, and then we have heard of NVIDIA, how to program that NVIDIA GPU and CUDA-based programming. And a lot of aspects has been covered in this workshop. What I will try to add in this workshop is one more aspect of quantum computing. That is, we can say, we could have said that it is a very futuristic technology, but right now we can't say, because this is at present happening. And we have the quantum computers which are working, and we can access over the cloud. So this is the present, and this is a futuristic technology where now we have to come together and bring this technology in the domains like agriculture, bioinformatics, and a lot of other areas where the optimization type of problem can be handled. So with that, I would like to start with a brief basic overview of the quantum computing, because I know the audience may be new to this aspect. So I would like to just give a brief glimpse of that, what is this technology and how this quantum computing technology is coming. We all know in the computer science that Moore's law is there, where the prediction is there that every 18 months this transistors, they are doubling, and then we will double those CPU capabilities. But now what we are seeing that what we were doing in a CPU, we were putting more and more transistors and making it more powerful. But looking at the size of that CPU, is it possible? Like when we are talking about transistor, there is a like PNP, and generally, when we talk about it is made up of a semiconductor, so there is a, you can see there are two different P and P. So there is one barrier. So this barrier, electron passes from this to this. When this barrier is there, it cannot pass. When this barrier is not there, barrier is nothing but a potential. So when we apply potential, electron cannot pass. When we don't apply it can pass through this. So it works like a switch. So this is a basic mechanism of a transistor. But now what is happening is this size is becoming very and very less. Now this length cannot be decreased further because electron then start showing the tunneling effect. So tunneling effect is very interesting effect that even if you apply the potential, then also the electron passes that gap. Now this gap, if we increase at that level where the electron shows a tunneling effect, then we cannot reduce the size below that. So that's why this Moore's law is failing. We cannot make now more and more powerful CPUs because of the limitation of the size and because of the tunneling effect. Now, what should we do? Because and the computing requirements are growing enormously. Like you can see, the biological systems, they are so complex. Plants, when we talk about the plant genomics, it is very complex, more complex than human being. We can say human being genome is very simpler than these plants. So to process that data, we need enormous computation requirement. Now those computation requirement, when we are talking, we need to find more and more new technologies that can fulfill those requirements. So quantum computing is one of this technology that provide this requirement. So when we are talking about quantum computers, they are based on the three basics phenomena of the quantum mechanics. That's why it's called quantum computers, because they are based on the quantum mechanics phenomena. What are those phenomena? Is a superposition, entanglement, and quantum tunneling. So when we are talking about superposition, it's a phenomena where, like in general classical things, we say 0 and 1. These are the two bits, and every computer, all the information is based on the zeros and 1. But when we talk about the superposition state, it says that 0 and 1 bit can be either 0 or it can be either 1. But when we talk about the qubit means quantum bit. So in normal classical system, we talk about the bits, but in the quantum computer, we talk about the qubits. So it is a quantum bits. And quantum bit, qubit can be 0 and both at the same time. So this is really weird phenomena. How can a person be both a state at the same time? So this is how actually quantum mechanics works, and it has been experimentally proved. Entanglement. So entanglement is another phenomena which we can see two different electrons. Suppose one electron having one spin, another electron having another spin. Even if we keep those two electrons at a very far distance, then also if we change with the spin of one electron, another electron spin automatically changes, even if they are at a very far distance. So what is this phenomena? So that's why these phenomena are very weird. I think Einstein called it a spooky action at a distance. So, and then quantum tunneling is actually passing the barrier. Like there is a very big hill, and if you make a tunnel out of that without climbing the hill, how to cross that? You have to make a tunnel. So electron similarly makes a tunnel and passes through that barrier. So this is how these three phenomena are working. So these are superposition, tunneling, entanglement, and based on this, all the quantum mechanical property is based. So what we are seeing here is actually, I talked about the qubit. So when we talk about the classical, it is like, to understand it, we can see that when we have a coin, either it is head or tail. So when we say head at 0 and tail as 1, but in the quantum qubit, it can be, if we toss a coin, when we toss a coin, it is in the space, then what is the state of the coin? Either it is head or tail. No, we can't determine it. So this is just to understand it, that when the coin is in, we toss a coin, then the state of the coin is actually a superposed state of 0 and 1, or we can say head and tail. So that's why qubit is also in a superposed state. And when the coin falls, and when we see, then we see head and tail. So similarly, a qubit, is superposed state of both 0 and 1. But when we see it, when we observe it, when we measure it, then only it can show one of the state, either 0 or 1. So that is the difference between a bit and the qubit. Now, why this is very important? Because when we are talking about the exponential increase in a classical bit, suppose there is a 2 to the power n permutation if you want to compute, then what is happening? We have to go one by one. So we have to say one possibility, second possibility, third possibility, fourth possibility. But in qubit, it is both 0 and 1. So we can measure all the 2 to the power n possibility at the same time because of the superposition phenomena. So based on these various phenomena, the quantum computers are being developed. Okay, so superposition, entanglement, and quantum tunneling. So we should remember that these three are the basic phenomena of the quantum computer. Now, based on that, there are various quantum computers, type of quantum computer that are being conceptualized. And when we talk about conceptualization, means there are many ways in a quantum computer qubit can be implemented. But the problem is the qubit interacts with other qubit and it destroys. So, and it even interacts with the environment and it get destroyed. So to maintaining the qubit state of superposition is very difficult. That's why we are having maybe right now what we are having different quantum computer, but they are having very less qubits. So now it's an engineering problem in those qubits in that state as a superposition. The more the time you, if you can make that qubit in the superposition state, the more accurate we will get the results. So this is how actually we have topological, we have adiabatical, we have measurement based, we have gate based. So there are various different computers available, and most popular one is actually gate based because this is a general purpose quantum computer. Now, quantum computer exists, and we can see that it is really having use, and we can use on over the cloud. IBM provided. There is a Rigetti company which is a commercial quantum computer provider, and then there is the University of Bristol. Then mostly it is being researched in the universities and then taken to the uh, various companies. And there are basically two types of quantum computer right now available, and there is a ion q also, so another type that is being developed. So gate based quantum computer are very much popular, and they are said to be actual real quantum computer where which follows the gate based architecture. And then there is a adiabatic based quantum computer that is supplied by the D-Wave. It is a Canadian company, and I think its client are Google, NASA. You can see a lot of client. It is there. So this is existing. So this is how actually a quantum computer looks like. You can see a lot of wirings, a lot of these things, and this is an IBM quantum computer called IBM Q. So you can imagine that this is how the quantum computer is there. So most of this thing that you are seeing here is a cooling, because we have to cool this to very low temperature, that is maybe minus maybe 5 millikelvin type of temperature, and you can see in between there is a one cylindrical structure. In that there is a small chip that is called as a quantum chip, and you can see there is a helium cylinder, and this is liquid helium, and it's cooled by dilution refrigerator. So most of the component you are seeing is mostly for cooling, and the chip is a very small chip that is inside this particular cylindrical structure. Why this cylindrical structure is basically to protect this quantum computer from various external interference like magnetic field, electric field, a lot of noise in the environment, a lot of radiation. So it can destroy the superposition state of the qubits. So to protect it, we have to give a magnetic shield, electrical shield. So those type of interference, for protecting that, this shield is given, and then it is cooled at very low temperatures, and finally at this superconducting temperature it behaves, it can its qubits are being implemented. So this is how actually it looks like, and this is real, and this is working, and it is available on the cloud. You can go to IBM and you can access it over the cloud. So this is how now what is our responsibility now? Quantum computer is available. It is increasing the qubit day by day, but our responsibility is that can we program it and can we use it for the applications like artificial intelligence, where quantum computer could empower the machine learning and AI, drug discovery, where we can simulate the molecules and we can find the structure. This is very helpful in the agriculture domain. This is very helpful in the healthcare domain. Optimization is a problem which everywhere it is there. Like we can see aeroplane, a lot of airlines are there. How to optimize the airline path or airline schedule so that optimum amount of fuel is being utilized. So this can greatly affect our carbon footprint. Then cryptography, how to protect from this everything is now in a cryptographic form. Our all banking transactions are depending on that. So this to make it more protected, and I think quantum computer also has a capability to break this code like RSA and those type of code. So encryption, if it can be broken by the quantum computer, then this is a very big threat. To protect it also, we have to use post-quantum cryptography techniques. So that's how I think this quantum random number generator and all those things are useful. So how to use our in all these applications. So this workshop is basically for the agriculture. So, and we can say that India is an agriculture-based country. How to use this quantum technology in the agriculture domain. So I would like to focus on this because we already knew about this agriculture, and we know that our land is reducing day by day because of the urbanization. A lot of agricultural land is being converted to the housing. So that's why various factors that are affecting the agriculture, there's a water, there's energy, there's a land, there's soil, nutrients, and biological system, and this full ecosystems, I think where quantum computing can influence, and it can play a very important role. So we discussed about this Envision 2030 that I think yesterday we have Karthikeyan sir. I think he talked in a very detailed manner about this sustainability model. So this sustainability goal, every country has to adhere by 2030. This is a UN envision where we have to provide the sustainable. When we talk about sustainability is development without affecting the future. Means or without harming the environment, without harming the nature, without making harm to our ecosystem, without pollution, without this type of. So can we do the development with a sustainability model where we can do the development but without harming the nature and uh, protect the nature for the future generations also. So this is how actually the major goal, and quantum computing can help very much in this aspect of the envision goal. Let us see how. Zero hunger, when we talk about nitrogen fixation, is a very important phenomena. When we talk about the zero hunger, we can see that there is a nitrogenous. So when we say nitrogens is a very important enzyme that is helpful in this nitrogen fixation. So it has so we can study these proteins like morpho protein, protein, and to analyze. When we are talking about nitrogen fixation, actually I want to just tell you that it is very important because the nitrogen that is present in the environment cannot be used by the plants directly, because there are triple bonds, and that is very much uh, hard to break. And there are natural like metabolites, organisms which convert that environmental nitrogen to the plant absorbable nitrogen. So this is a very important nitrogen fixation process where nitrogen is one of the enzyme that helps. So a lot of study are being done, but the phenomena is really a mystery. So to understand it more easily, I think quantum computing can help. So in that way, our what quantum computer does is actually mostly optimization techniques. So can we find an optimal energy model for this type of molecules, this type of proteins, so that this can help to understand the nitrogen fixation phenomena, and then we can do it more in a economic way, or we can do more in a ecological way. So this is how this nitrogen fixation can be very important. Another aspect is actually carbon footprint reduction. So when we see lot of pollution is there and mostly carbon dioxide is there, so can we convert carbon dioxide to some other compounds? So when we talk about this in a catalytic cycle, there's a paper, I think, and ruthenium based catalyst react with the carbon dioxide and hydrogen molecules to produce water and methanol. So this is a very big thing. I think if we can study it more and we find out that how this carbon dioxide can be reduced from the environment, then but these both the problems that I have highlighted here, one is the nitrogen fixation, another is the carbon footprint reduction. They involve with the molecules, they involve with the proteins, and that are very complex structure. And on a big supercomputers itself, it's a big challenge to solve these type of problems, because these molecules, suppose when we say a protein, even the folding, how a protein takes a shape, this is a protein folding problem, that itself is not solvable by the current supercomputers. Even the biggest supercomputer can't solve this type of problem. So for that aspect, since quantum computer shows the exponential power with the qubits and with the superposition, can these things be done on the quantum computer? So mostly when we talk about the quantum computers, they are very good in optimization problem, solving optimization problem. And most of the problem in this world which we are dealing with are basically optimization problem. So when we see a protein takes a shape, so there can be millions of orientations. So why the protein fold in that particular shape? So this particular thing, if we understand, there are millions and millions of ways it can be done. So classically what we can do, we can just start from one way of folding, then we say, okay, this goes to this shape, second folding this go to that shape, third folding this go to third shape, and we have to do one by one sequentially everything. Even we parallelize this thing, then also we need a huge computation power. But in quantum computing, like in body, our human body, this happens in a fractions of, means we can say microseconds. So how our human body does it? So that the concept is that our human body is basically a quantum body. Our brain is a quantum computer, and most of the phenomena in our body are having at a quantum level. So if we can mimic our body behavior using any external atoms or photons or any other devices that are in the nature, can we mimic our quantum phenomena on a quantum computer? So when we say quantum computer, is means implementation of qubits, and that can be done on any of the atoms, on the photons, or any of the natural minute particles. So can we do that? So based on this, we have developed quantum computers, and these optimization things like various energy levels, and which is the energy that is best suitable for this particular shape, we can find the minimized energy level, and that is the perfect structure. So these problems we can take it as a challenge. Now what is happening, already we are very much behind, because a lot of countries, they have started working. US is much more, they have very aggressively, they are funding this things. And then when we are talking about China, it is being investing in hugely in this quantum computing area. So we have to start, and I think we need young people who can start thinking in a quantum way. Like we can have same algorithm we were talking about machine learning, we can have quantum machine learning. There are in fact a quantum zoo. So if you go on the internet and if you see, there is a quantum zoo where we can have 400 algorithms already implemented. But can we implement it on a computer and there are quantum simulators also available. Can we code it? Or even if you want to run on a quantum computer, IBM quantum computer cloud-based access is available. So can we run on an IBM quantum computer? So all these things I think can be taken forward, and based on that, I request all the students that they should start thinking in a quantum way, because the future is quantum, and it will definitely help in the agriculture, and it will definitely help in all other associated fields like drug discovery and various problem related with the optimizations. And it can solve a lot of challenges that we are facing. So with that, I would like to complete my talk. So we have to now move toward degenerative to regenerative agriculture. Thank you.
Thank you very much, sir, for a nice presentation. As of now, I cannot see any question, but there is some good comments. Vishwajit Ray is writing best webinar on quantum computing.
Thank you so much, Vishwajit.
And I want to add one thing in this, which is also associated with quantum computing, as a famous statement given by Richard Feynman. If you think you understand quantum mechanics, you don't understand quantum mechanics. So it's already, it can be associated with the quantum computing also.
Yes. So I think it's a very complex field, and I think we have to come together. We have to collaborate, and with like scientists like Milind sir, we have to understand the problem. We have to various scientists of the agriculture domain. I think the beauty about this workshop is that we have brought some of the eminent scientists from the field that are working in the agriculture. We have brought some of the eminent scientists from the chemistry level, like we have Karthikeyan sir with us, and we have brought computer science people together, and we have also brought many of the decision maker in this, so that we can come together and try to solve the problem that we are facing. Grand challenging problem should be faced, because now it is not a time to solve the small problem. We have to face the grand challenge problem, and for that we need grand infrastructure for that, like national supercomputing mission. We already have a lot of supercomputers, and these supercomputers can be used to solve the agriculture problem. So we have to now define a very big roadmap so that we can conceptualize agriculture grid, a Indian national agriculture grid, so that we can solve this grand challenging problem, and we can include the quantum computing part also in that, so that this type of problem can be solved.
Thanks, Amit. It was a very
There is
interesting
one
talk,
question.
and with the National Agriculture
There is one
Grid, this will be very useful
from-
for researchers and for the farming system. So thank you very much.
Thank you, Milind sir.
So
Yeah.
there is a one question from
Samit,
agriculture
and
student.
got to know about this innovative things happened in India. Quantum computing initiative has been already been taken by Government of India, and you have given a brief summary that what initiatives and focused on that how government is going forward. So thank you very much, and I am hoping that it is triggering something in the mind of participants that they start studying about quantum computing in the world, how the happenings are occurring.
Sure.
Ma'am, related to that, there is a one
Thank you.
question from Vatsal Pura.
Yeah, please.
He is asking.
Om Prakash, you are not clearly
Yes, ma'am.
audible.
Yeah, what he's asking a question.
Ma'am, there is
I can hear you.
Yes, sir. However, indirectly you have given answer of it.
Yeah.
How do agriculture graduate start with quantum computing?
Yeah, I think first thing is that to start with, you don't need anything. Just go search IBM Quantum. You create your account, and there is a very good documentation of Qiskit, and you just read it and you start programming. Your first code you can write very simple way. So this is the first start way, very easy, and all the students can do it. It is freely available.
Thank you, sir.
Thank you, Amit sir, for your wonderful enlightening words. Now I would like to welcome our new speaker, Mr. Naveen Tabrakavi, and I would like to request Dr. Neha Bharal Madam to kindly introduce our new speaker. Thank you.
Thank you, Nilesh. Mr. Naveen Tarvakavi is a research scientist at IBM Research Lab, India, focused on climate change, sustainability, food chain supply, and agriculture. Within these domains, he has over 15 years of experience in research and innovation. He started his career as an assistant professor, where he focused on sensor development, report sensing, crop modeling, and data analytics for agriculture and environmental applications. During this time, he successfully uh, judged several projects for organizations such as NSF and USDA. For his research contribution, he received the Early Career Award in Soil Physics for the year 2011. In 2010, he joined the Desert Research Institute as an associate research professor. At DRI, Mr. Naveen has researched on remote sensing application for water resources and agriculture management. He researched on the leaf clip sensor, which measured transpiration from a plant in the real-time manner. He also worked in aeroponics and was an advisor on hybrid crop growth technology. Mr. Naveen has advised intergovernment organizations such as FAO, WEF, among other, on the future agriculture, environment, and supply chain. With this, I would request Mr. Naveen to please share your knowledgeable words with us. Thank you, sir.
Thank you, everyone. Thanks a lot for having me in the meeting. Let me share my. I was having trouble connecting, with the internet. Let me share my screen. So what I'll go through today is some of the work that we have been doing at IBM. And I'll try to provide a brief overview of the thought process behind it, and then provide some examples of what we have been able to do already, right? So with that said, let me set the stage for what is it that we are trying to achieve here, right? So, I mean, agriculture, the source of all food supply chains is the practice that the farmer does. And I'm hoping you're all able to hear me.
Yes, Mr. Naveen, you are clearly audible to us.
Okay, thank you. Okay, great. So, it starts with the farmer, plowing his field, and and then the food supply chains are built on top of that, as we all know, right? But if you consider 20 years back, where the climate was not really changing, and the seasons were coming in more or less in a cyclical way. Even then, farming was very stressful for the farmer. There were all kinds of problems that you could face in the season, and this led to a lot of uncertainty. Right now, just to accentuate the problem, now we have this whole issue of climate change. Right, so there are multiple reports. Even our own research has shown that what we thought of a season is probably no longer on those months. A season for maize seems to be shifting, and these shifts happen in their own way. So there's a climate change effect that is happening, and it is manifested essentially in two ways. I'll describe that later. But that is something that we have to now further comprehend, right? So with more uncertainty at the farmer level, the question now is, how does that have a ripple effect on the entire supply chain? So with that said, the key question that that a private sector might have, or the government might have, at a downstream of the supply chain is, where can I actually place my bets? If I talk about corn example, what is going to be the expected corn? What is going to be the quality of the corn that I can expect from Karnataka? And if so, what is going to be the spatial aspects of that? And so this is a kind of a question that's becoming more and more uncertain, right? And if you think about all these procurement centers, a lot of pre-planning goes into play. You need to have transportation contracted to people. You need to have the right amount of warehouses ready. So without this kind of production forecast, it can become quite a nightmare, right? So you might either have excess of of the facilities or in, under availability of the same. So if I have to say, if I take this question and then say, okay, how can I address this? And if I start mapping it out, what we'll see is, we will essentially see that uh, your entire region might then be broken down into different levels of resiliency, right? So there will be some areas for a given season which would do a good job, and then there will be some areas which will not do a good job, right? So, and this could be picked up with, let us say, using weather forecast data. But an interesting challenge comes up, and that is this whole idea of extreme events, right? I mean, if you think about the manifestation of climate change on agriculture, it comes through two ways. One is by changing the temperature and precipitation pattern across the season, and the second way it can affect is this sudden occurrence of extreme events, right? So there have been, I mean, more and more we see these examples. Perfect season all along, and right towards the end, you have a flood event happen, or you have a heat wave, or you have a cold wave, right? So not only do we have to consider the changes in the weather during the season, but we also have to know when an extreme event would happen, and that has to be accounted for. The challenge is extreme event prediction is not as simple as trying to predict weather pattern, and lies a big problem. So we have to, and the most event risk, and therefore not a good area, if you're a procurer or if you're a government, kind of ensure that more insurance is sold in those areas, things like that. So you need to come with better plans, right? And then, so you'll have these kind of areas. Then there will be some areas, where when we are trying to predict, it's just the fact that the uncertainty of the weather in the upcoming season. So if you think about weather forecasts that we get today, they come in ensembles, right? 50 ensembles for the entire season. And the spread of these ensembles could be so much that we might not be able to put a finger and say, this is going to happen, or the production will be in this ballpark. We would not be able to say that. So this has this area where with this vertical lines, is an illustration of you will have that kind of areas or locations too, right? Now, the interesting or the challenge for us is to be able to break down any given area in a country and say, which are resilient areas, which are resilient, but I don't know about the extreme event risk. And then, of course, which are areas where, the weather is too uncertain, and therefore, we all better, watch what we are doing as the season progresses. So this is more and more of a problem that's coming up, and we are seeing this play out. And what is its effects on the way the government does things today, right? So what I have here is a extremely bad representation of what a season looks like. But think of this as, you have a sowing window where farmers are sowing. Then, after a month or so, governments put out these sowing reports, banks put out these sowing reports, and you have the season going. Let's assume you have a 6 or 8 month season. You have a mid-season survey sometimes, and then you wait for the harvest, and after the harvest you have these harvest reports, right? And so if you look at the current state of the art, not just in India, but I would also say in the US, is that the traditional reporting goes this way. You have these sowing reports, you have these mid-season reports, and you have these post-season reports. Now let's come from backwards. Post-season reports are too late, if you want to plan, right? Because it's already over, it's already done. Mid-season reports are very, very survey heavy, and therefore, yes, you will have some nice points of data to ponder, but you might not necessarily have a complete distribution, right? And then the sowing reports are good in the fact that you will have how much area has planted and so on, but it's not, you can't use that to project what can be the production, right? So an ideal scenario where we would want to, which we would like to have is something like this, right? So we start with the season, and we get these reports of what is the area under production, but also what is the expected yields. And these reports, if they come every month as new seasonal forecast data come in, either through ECWF or forecaster sources, we have error at the start of the season, it will be, it's good to know, right, what you can expect in terms of spatially, in terms of the total amounts, right? And then this kind of, ideally, if it converges towards a certain value as the season progresses, then as a government, as a private sector, we would be in more control of what we will be doing, right? So that's essentially the ideal way that we envision at IBM for helping the supply chains. And to kind of cover that, we have our own the solutions that we have built. The bottommost row of our solutions is what we call as this future of climate innovations, right? And so within these innovations, we have work going on with where we are using AI-based methods to do seasonal forecasts, to do extreme event modeling, and I just want to state some interesting things here, right? For example, seasonal forecast, right? The traditional way to do seasonal forecast is, is to run these process-based models, and have this 50 ensemble model, that you then use to kind of sense, where the weather is going. What we are working now is get away from the process-based models, but get more into things like how can we use what we call as sea surface temperatures, variation across the globe to actually make a seasonal forecast, right? So to get away from the process-based models and just purely go from satellite data and then see how we can project the future. So interesting things like that. Extreme event modeling is a very interesting part. I mean, extreme events like droughts can be easily predicted, I would say, relatively, because temperature is the key variable there. But the challenge is, how do we go about predicting things like floods, right? And within floods, you have two kinds of floods. One is what you call as the pluvial flood, which is basically inundation of land because of heavy rains, right? And then you have something called as the fluvial flood, which is inundation happening because of the river network, right? So I know how do we go about doing these two kind of flooding models, and so far this has been limited to what we are trying to do is that make it available to everyone to use that data, right? So that's another section that's going on. We have coupled that with our environmental intelligence suite, which has a series of data on soils, on global crop calendars, and agronomic practices. And so we combine these two sets of information at the bottom layer to process-based models, ML-based models, to actually project and forecast what could be the expected yields or production in different regions. So that's essentially the second layer we build on top of this. So the way this would work is, we can either do it, with very minimal information. But if somebody comes and says, I have district level production data for my region, then we can further improve the model through some kind of a transfer learning approach. So that's essentially the second layer. And the third aspect is, AI is only as good as the way we use it, right? So what we are also working on is things like, if I as a government want to know, which regions are going to perform really good in maize this upcoming season, so you can rank them, right? So we can rank our different supply regions. We can discover new regions. So let us say if you are a company trying to procure maize, and your traditional area has been, let's say, state of Karnataka, but then you want to know, are there any regions near my procurement area which are going to be more resilient in the near future? That is something that we can also do, right? Because the method itself is scalable. So on top of it, we're making tools for decision making, pre-season planning, so things like that. Also visualize the forecasted supply. And so these are the production related tools that we're building for the business cases. But then there is one more additional element which is becoming more and more important, and that is, or this entire production forecast or yield forecast with resiliency or sustainability, right? So we are the data from this work essentially then kind of feeds this carbon credit innovations that's also going on at IBM. So I'll show some examples. This presentation is more example heavy because I thought let's it's always good to see the examples and then understand, okay, this is the kind of things that can be done, right? So so with that said, I just want to quickly capture the method itself in a very wide way. So so if you think about how weather affects crop production, and climate change manifests its effects through weather, seasonal weather, right? So if you think about how the seasonal weather is going to affect, there are essentially two pathways to it. Now, one is what we call as weather pattern changes that happen because the plant growth process is inhibited. So for example, high temperatures, lack of water, right? So drought kind of situations. You have yield by actually efforts plant grow and so on. Other way is, the plant might be perfectly growing, but you could have these extreme events that kind of hurt the crop from the outside, right, rather than from the inside. So for example, things like wind gust. I mean, Tamil Nadu is a great example for that, right? I mean, a few years back in Kanjipuram, there was this really good production of rice going on, but then there was almost cyclonic winds that kind of eliminated the crop right at the harvest stage, right? I mean, you really couldn't do anything about it. So so this wind gust could be an impacting factor. Wildfire is not as much of a factor, but things like flood can also become very important. Now, again, the flood could be pluvial flooding, it could be fluvial flooding. And last year we had a good example of fluvial flooding in Bihar, where multiple rivers kind of inundated, even crops like rice. I mean, which love inundation, right? I mean, even those were kind of affected. So this is the two pathways that it affects. So the way we kind of took it upon ourselves is, okay, we took the seasonal forecast. We have these physics-based models that run or actually capture how the crop is going to grow. Then we kind of couple that with extreme event forecast data that then are combined to become a part of the entire ML driven approach. So we use the physics based models to capture the systemic loss of yield through the crop growth, but then we also use our extreme event data, and then both of these things are brought together to predict our forecast, right? So with this said, let me just go through a few examples and just want to talk about how we can use this method for multiple cases. Now I'll go with the first one, the data rich situation, and this is predictions for the entire corn belt area. Corn belt grows their corn in US. This is in the US, and they grow their corn start around April, May. They sow and they harvest around November. And so what we have count, what are the yields most likely going to look like, right? So, so this is for the 2021 season, and we project the yields every month, and we also at each pixel also provide a coefficient of variation so that you know what's most likely the value, but then you also know the uncertainty bounds about it, right? So this could be done for anywhere in the world. So this is just one of the examples. So to just demonstrate that, this is again the same data, but then we aggregated the values at the county level, right? So that's for this current upcoming for the season. So this is for March. Now we do this for every month until the season essentially ends, right? So we also did the same thing for a poor data available country like Rwanda and Burundi, right? So here again, we basically predict the production for various years, and that's the actual yield and average. So these are two countries which where you have very few data points, an interesting output of this work is, you can actually come up with these maps. And what these maps essentially tell us is which parts of the country are expected to perform in a certain way. So, so in the case of Rwanda, we identified that there are like two type of areas in terms of corn, maize or corn growing. Whereas in the case of Burundi, there are three zones, right? And now these zones will change from season to season, and we can update this every month as the season progresses. And if you think about yourself as a procurer or as an insurance company or as somebody who's interested in sales of inputs or even as a government, right? So I mean, we can then figure out where is the right place for me to be active, where where can be doing more extension services. What kind of knowledge should I be sharing in these three regions? Because these regions are based on the nature of the growth that is expected. So in the case of the Burundi, if we have three, the one in the middle was supposed to have very drought-like conditions. So if I were the government and I had my extension officers there, I would pay more focus on stressing on the use of water, on stressing on the right timing of fertilizer, and so on, right? So this kind of targeted work we can do upfront in time, and then make it happen, right? So this is one example. I have another example. This is the case of Karnataka, right? In Karnataka, we have this forecast, the maize arrivals at various procurement centers. So what we have here is for some of these centers. So as a part of this work, what first we did was, these are the black dots are all the procurement centers. We have to first, create watersheds for this dot, for this black procurement, the procurement centers. Right now, there's two ways to do it. We can do it as the crow flies, right? So we can say, wherever is the farmer the closest to, he will go to that procurement center and then sell his product there. Another way is, you can go by distance, right? You can look at the travel time. You can look at the actual distance traveled through the road network, and that's another way to do it. So we have both the methods. So this one, that's what you see is as the crow flies, right? So that's why you see these nice straight lines of division. So we divided the entire area, and so we start before the season. Now for some of the this one, so what we are projecting, and on the end column you'll see the actuals, right, for the last year, and you'll see that we are converging quite well, right? So if you think about the same table here, this is exactly what I was mentioning. So when you start the season, the error is kind of high, and the 20% ballpark, but as the season goes, it kind of converges, and that's what you expect, right? So so this is essentially another example, where you can take this idea and then use it for for a larger goal, right? So that's one more. Let me talk about another. I kind of find this example to be interesting because it has an effect for one of our clients. So we'll talk about this. This is about procurement at a sugar mill in Thailand, and what we did here was, this is the one of the provinces. This is the mills that and this kind of a lot of the sugar they must have. And the idea here was, I am a sugar mill here, and I know that farmers come to me, within a 60-kilometer radius. But sugar cane being sugar cane, a long crop, more sensitive to water, and knowing the fact that there is competition from other sugar mills, which parts around me should I be targeting, right? So, should I be more focused on farmers and villages that are to the northwest of my sugar mill, or to the northeast of my sugar mill, right, or the south? So, which is the direction where I should be looking at, right? That's exactly what we tried to do. We took our method, and we started to forecast what is the relative yield around the area. So this is the sugar mill we have, and you can see here that different levels of procurement potential, that you have from that particular mill location. So one darker means better, if not, lighter is means very poor potential. Now, if I take this and then overlap with the other sugar mills, now this presents to me a very interesting scenario, right? You'll notice here that there will be some areas where there will be high production and a very low cost of marketing. That's because this area just happens to be closest to your sugar mill, right? So if I take a look at that, you might end up, identify some areas like this, right? And then there will be areas, where there'll be high production but very low return on marketing. That's because, because of the competition from other sugar mills, right? So you can do the same thing, and you can identify areas like that. Then there'll be areas which are good production potential but would have a medium return on the marketing. So you can identify the same, and then you can do the low ones which you want to maybe ignore for the upcoming season, right? So this is what kind of things we can do. Now this is a very private sector example, but there are lots of such applications that we can do. Especially crops such as wheat and rice that are procured and then stored. So we can, for example, expand this example to identify if I were to build new warehouses, government warehouses, or if I were to build new cold storage areas, what is that right location, right? Which at a very minimal cost to the farmer in terms of transportation logistics would serve the purpose of the community, right? So if we want to do work like that, we can take our approach and then project this data 5-6 years into the future, and then kind of make some kind of data-driven, explainable, identification of locations, right? So that's essentially what we could do. So there are many ways that we can use the model. I think carbon yield, right? Use our model for that particular work, right? So, the interesting part with this, combining production forecast, that means how much am I going to produce in a given season, with carbon emission, is the fact that they are not linearly separable. They are very much intertwined, right? And for example, you might get an amazing yield by applying, good amount of fertilizer, but then it will have a negative effect on the carbon, on the carbon sustainability side. So you'll have more emissions, right? Because because of the GHG emissions from the fertilizer, exposure to the atmosphere. So on the other hand, you could, for example, do no tillage, right? Which is really good for sustainability, but then you might end up with a relatively less yield, right? So how do we understand the trade-offs between the carbon emissions and the yield is one question that is very becoming more and more important as we speak to our clients. The second aspect that becomes more and more interesting is this whole idea of carbon credit market. I mean, it's becoming a big thing, right? And companies are wanting to buy the carbon credits, but where should I be targeting, right? I mean, the challenge with this whole carbon credit market is there's no way to measure. I mean, even if there is a way, it's not very scalable. So how do we know which areas should I be targeting this upcoming season, wherein the farmer will be motivated to sell me credits because it doesn't hurt his yield too much, when I force him to adopt a certain method, right? So these are the kind of questions that becoming more and more important. It's already important, I would say, in places like US, and it is starting to become important as we speak in India as well. So this is a question that we wanted to kind of address. So the way we do it at this point is, we take the yield forecasting at the regional level, and we have a AI-based emission and yield optimizer model. So what this model does is it uses what is projected yield for the given region, and then tries to predict or figure out what is the most likely fertilizer usage of the farmer, right? And And from that, we can do two things. We can actually estimate the emissions, and we can also estimate the expected fertilizer pattern that can be that most likely is going to be seen in the region. Right? So that's essentially the background for this work in terms of the methodology. So we know we again did this for Iowa. So this is an example of revenue from yield for one of the cases, and this is the revenue from carbon credit. If you assume $12 per ton of carbon that was sequestered, and this is the net revenue. So few things to observe is it's not like there's a perfect trade-off between yield and carbon credits. It's not like they go opposite to each other all the time. There are some areas where they both go in the same direction, right? So, and then there are some areas where they go in opposite directions, right? So, and this is very much functional on the weather itself, right? You cannot put it as a one answer for for a given crop for a given area. This changes from season to season because, and therefore how the fertilizer is going to be consumed by the crop is going to change. Therefore, the sequestration and the so that's what we tried. We got some very interesting and some good validation that we saw, right? So this was another quick example that I wanted to kind of showcase. So last but not the least, I just want to also talk about, so far we talked about, production, right? We talked about, how can we forecast the production at any given area and so on and so forth. But then the challenge is, if you're trying to, for example, think about the supply chain point of view, production is just one node, right? I mean, the produce travels from the farm gate to the silos or the warehouses, and then from there, it moves forward into wherever it is going. And weather has more and more of an effect on each of these segments, right? And case in point is that famous example we had a few months back in Suez Canal, right? I mean that was carrying a whole lot of goods from Europe to the rest of Asia, and we all know what happened. It was a wind gust, and a pretty powerful wind gust, and that's essentially kind of resulted in billions of dollars of loss, right? So if I were a company, or if I were a government who was procuring things or critical supplies from outside, yes, what is the sustainability and what is the expected production at the source is important, but how safely can they come to my location is another aspect to also consider, right? So that's essentially what we are also doing. So we can map out the production forecast for any given location, but then depending on where the procurement the warehouse is, we can actually figure out how much of travel time it's going to take, what is going to be the food loss and waste as this thing is being transported. So as an example, imagine a truckload of quite a decent amount of strawberries sitting in that Suez Canal ship. That's a significant loss, right? So there's going to be a lot of food waste because of the extra time. So all of these factors, and then there is of course a carbon footprint during the travel that also needs to be considered. So this is another work that again uses the extreme event forecast data that we have developed at IBM Research, and we can make this kind of work happen, right? So I think I am like way ahead of my time, but I think that's what I had for today. I hope the organizers won't be unhappy if I yield some of the time back. Yeah, so I'm open to questions. Thank you.
Thanks, Mr. Naveen, for your wonderful talk and sharing some of the thoughtful projection in terms of research in the agriculture. We have few questions actually. So Mitali
Sure.
Roy has asked a question. Since Zombium is only present in exclusively in some specific plant, root and algae, can we produce clearly artificial fertilizer to meet increasing supply demand using quantum computing?
Yeah, so that's a very forward-looking question, right? So I mean that's great. I mean, I think quantum computing we have to be, I would say, it definitely has a lot of potential, but in terms of real-time applications, we are still getting there, right? We are not yet there, and right now the core algorithms are being developed and so on. So I think. Quantum computing itself might provide us the answers sometime I would say in a decade or so. But I think the more interesting question that I think Mitali asked is this whole idea of cleaner agriculture, artificial fertilizer, right? And this IBM has this idea of 5 in 5. So every 5 years, we come up with the top 5 items that we want to work towards, right? And very interestingly, solving the fertilizer problem actually features in one of those 5, right? And why is that so? Because if you think about nitrogen fertilizer, a lot of it is lost through ammonia, and that's not necessarily a good thing, right? So what we are essentially trying to also work on the material discovery side is how can we motivate ourselves from the way soybean, for example, fixes nitrogen, right? And what are the requirements that would be needed? So that work is going on, and I feel pretty confident that we would have some kind of an amendment to the soils that we could add later in the future that would fix the nitrogen, rather than you or a farmer going and buying the fertilizer for himself, right?
Thank you, Mr. Naveen,
I don't know
for
if that
addressing
answered
the
the question.
question. Yeah, we have another question to you. What model used for before sowing, growing stage prediction of the yield?
Great. So the model architecture is very similar, right? So we have essentially the model basically takes data from two branches, if I may say, right? And the first branch is the physics-based models. Now we can also replace those physics-based models with AI-based models also. In the case of physics-based models, we were inspired by the Worforce methodology, right? Largely because it is scalable and it's easy to incorporate. But then we made some amendments on top of the Worforce model to make it happen, right? So that's one thing. On the second branch, where we get the extreme event data, we have two approaches. One is use the seasonal forecast as it is that you're getting. Another is actually use the sea surface temperature maps. And why sea surface temperature maps? That's because the sun and the earth, it heats the land. All the weather we see is basically a manifestation of the sea temperature, over time, right? So one thought we had was, why use the seasonal forecast data? Why not just use the prime source of the weather itself, right? Which is the sea surface temperature and the land surface temperatures, right? So that's another way we incorporate. And these two, and the structure is the same. No matter if it is before sowing, after sowing, in season, the same model is used.
We have another question from Rahul Kashyap. Which extreme event is impacting the IGP croplands?
IGP, if we could expand on the IGP, and I'm sorry, I'm very bad with abbreviations. So, yeah. I mean, but I can talk in a more general sense, right? I mean, extreme events. There is a lot of work, where they looked at what extreme events are very important, right? In terms of our inability to capture it, right, and understand how it affects the crop. And so right on the top is essentially floods, right? I mean, floods and precipitation. Now, this flood could be two ways, either because of heavy rains or either because of fluvial flooding, water coming from the rivers, right? That is the number one, by far, the biggest problem that has been identified. Now, after that, it is basically very interestingly is hail, right? Hail has a lot of significance in the agriculture sector because it affects the cash crops a lot. I mean, you go to Himachal Pradesh and you talk to apple farmers. The number one problem is this big hail and destroying their apples and their flowers, right? So you come to North Karnataka, same problem. And drought, right?
Hello, Mr. Naveen, your voice is breaking actually.
Yeah. Can you hear me now? Is it better?
Yes, yes. So the last question we have is, does IBM offer any opportunity for agriculture graduates for modeling and precision farming?
Definitely. I think agriculture is a very important field. I myself am an agriculturist. I'm a soil scientist. But I think the right way to look at it is, think of ML and AI as tools, right? And if you think of ML and AI as tools, then everybody needs tools, right? So it's not just the people in the tech world, the pharmaceutical industry, right? It's everybody needs tools, and more so with agriculture. So if you take that perspective, then somebody can make themselves very attractive, for companies to recruit them. Yeah, that answers the question.
Thank you, Mr. Naveen, for addressing all the questions raised by the participants. Thanks again for accepting the invitation and giving the wonderful talk.
Thank you.
So let's move on to the next speaker. We have Professor P. Ganguly. So I would request Dr. Tiwari to please kindly. I would request Dr. Tiwari to please kindly address Professor P. Ganguly.
Yeah. Next speaker is with us. So, am I audible?
Yes, ma'am.
Yeah. So, Dr. Ganguly is an assistant professor of land and water resources engineering specialization at the Agriculture and Food Engineering Department, IIT Kharagpur. Dr. Ganguly received PhD from Department of Civil Engineering at IIT Bombay, and MTech in Water Resources Development and Management from IIT Kharagpur, and BTech from University of Agriculture Sciences, Dhanbad, in Agriculture Engineering, where she was the recipient of the University Gold Medal Award. Dr. Ganguly works at the intersection of hydrology and climate extremes, natural hazard resilience and water sustainability, computational data science. She was in the section hydrology division at Helmholtz Central Potsdam, Germany, as an Alexander von Humboldt Early Career Research Fellow for 2 years. She was a postdoctoral research fellow at Sustainability and Data Sciences Laboratory at Northeastern University, Boston, and McMaster University, Canada. In her early career, Dr. Ganguly worked as a patent analyst at a Swiss-based multinational firm for about a year. She is the associate editor for the Water and Built Environment of the Frontiers in Water Journal. So welcome, Dr. Ganguly. Please start your talk. You are not audible. Dr. Ganguly, you are not audible. So her title is Big Data and Natural Hazard Modeling, Challenges and Opportunity for Machine Learning.
Not audible, madam.
No, madam, you are not audible. Your slides are visible earlier, but now that is also not visible. So what you can do, you can share your slides again, and maybe you can call our mobile and we can have audio. So slides are visible. Can I think anyone call Dr. Polame, and then audio can be heard from mobile?
Yeah. Let me check her number.
Dr. Pauline, can you call Dr. Aruna on mobile so we can have audio from there?
So, madam, you can disconnect and then connect. Let's try.
डिस्टेंस का थोड़ा और
Madam, we are audible to you?
Can you call on mobile? Can you?
We are actually not having number. I am calling Professor Pabitra.
Yeah, we can see you, madam. Can you unmute? You unmute, madam. Actually, you are muted. You just unmute yourself.
Yeah, yeah.
Yeah.
Madam, you please type your mobile number in chat box. I'll call you. What's the problem?
Yeah. So we can have audio over mobile, and please share your screen, madam. Your screen was visible, slide were visible. Yes, your slides are visible. You can please speak on mobile.
Yes, madam. So I think Amit is audible to you.
Dr. Arun, you can keep the mobile in loudspeaker mode with your mic so we can hear her.
Yeah.
Dr. Aruna, kindly unmute yourself. You are muted again. Dr. Aruna, please unmute and you can keep the mobile in loudspeaker mode so that we can hear Dr.
Yeah,
Folemi.
yeah. Actually, her phone is engaged. I think she misunderstood. So I'm again calling.
Okay.
Hmm. Actually, she is trying with the one more mobile she's having. So she was trying to connect with different mobile. So I given the solution. She'll take some time. So Dr. Om Prakash, meanwhile, any message for participants? Dr. Om Prakash?
So we can tell about
Yeah,
the
sure.
certificates.
Yeah, that already mentioned in the morning. It was every 1 hour that message is displayed on that YouTube. That fill that Google form, feedback form. Yeah, so madam called me.
Yes, yes. So you can put on loudspeaker.
Yeah, madam. Yeah, I'm switching on my speaker. Yeah. Yeah, speak something, madam.
Okay. Hello.
Yeah.
So is it audible now?
Yeah. Yes, yes, we can hear you. Please continue.
Sorry for the disruption.
Now, why this?
Yeah. So I think two devices, that's a problem, I guess.
Are you connected with two devices, madam?
Okay. Now. Hello.
Yes, yes, you are audible. Please speak.
Okay. Anyway. So one is doing the.
You can mute your laptop. In the laptop, where your slide now, you can just press the mute button.
Yeah. So is it okay now?
Yeah, it is echoing.
It is echoing actually. Live stream में और problem होगा ना?
So are you using a headphone or you are directly connecting with your laptop? Hello.
Yeah, Amit, she is directly connected to laptop.
So then her audio is coming, I think, directly also.
Let me switch off this speaker. Okay.
Hello.
Yeah, madam. Yeah, please speak, ma'am.
Please speak, madam.
Madam, please speak something. I think audio is coming from your mouth. No, it's not coming.
Or let us continue on the mobile. It is understandable. Means it's not so much. You can dial her.
1 minute, ये विकास is giving some solution. विकास कोई solution है तुम्हारे पास? So my scholar is calling you, madam. I have given number. He's saying that you need to install that WebEx app on your mobile. Then this echo will not come. So he's giving you solution. He will be calling you shortly.
Hello. Can you know my laptop? I'm Amit here.
Yeah, Amit, actually Vikas called me. So he told that madam can download that thing, WebEx
Madam,
on some solution he's giving.
let us try with my mobile.
Okay.
Okay.
Sure. Okay.
I'm sharing her number.
Sharing her number.
Yeah, I'm already connected with you. Please mute, madam. Aruna, madam, you please mute. Yeah, please speak, madam.
Thank you. Thank you. So I will start with slide over.
Madam, your laptop audio you reduce.
Hello.
Yes, yes. Please start.
Okay. So what are the challenges and opportunities for the machine learning technique in the natural hazard assessment that I'm going to speak in today's presentation? So first is water in 21st century. Why we should concern about the water in 21st century. So the global risk report, 16th edition, you can see here, this is the, according to the World Economic Forum, so you can make it diagonal. So at the lower end, it is the lower risk, and at the upper end, it is the high risk zone. So in the high risk zone, if I increase it here, so if I zoom this portion, so you can see that extreme weather, the natural resources hazard, and also climate action failure, infectious diseases are the greatest risk of today's 21st century. And according to the Red Cross Society, there is a clear tie between today's extreme events and the human causes. So this we can see here. So the climate action failure is one of the greatest threats of today's century. So now, some other aspect, if we see here, the other aspect, how the different interconnected and the cascade hazards affect the large-scale infrastructure system. So, for example, here the heat wave, and then the drying of water bodies, and water demand at the agricultural sector. So, when all these factors interlink together, the severe, so for example, here the severe heat, water stress, so that is actually a threat to the power plant sector. So here you can see the sparser and warmer available water that leads to the more extreme impact. So based upon this, we can make it water stress map so that we use in our study in United States. And here you can see that some of the counties we have identified. So some of these are identified here, and here you can see the stream temperature, which exceeds the significant the that is the percent of something of the stream temperature. So if it exceeds higher than this, that leads to the failure of the power plant operation. So that depending upon this, so is it not audible? Hello, sir.
Yes, yes, you are audible.
Okay. So the partial water, the normal water is actually reached to the correct to the power plant sector. So based upon this, we have identified some of the stress regions. So now take an example of the heavy precipitation, river flood, and also the coastal storm surges. So this is actually ongoing Indian condition. So now if it has a heavy precipitation and the river flood, if it is coming at within a certain time window, say within a week of occurrence, and the storm surge level. So now there is also the tropical cyclone phenomena. So that leads to the storm surges at the coast. When the storm surges and the sea level rise again interact along with the river flood, that creates an extreme impact. So one of the ways, the non-structural measures to assess this kind of a risk or reduce the risk is to make a inundation map. So flood zone delineation based upon this inundation map. So when we identify when we delineate the risk or the hazard, we have to consider all different components. For example, the probability of hazard, as well as the inundation, and also an impact multiplier. So all these factors is going to affect the risk map. So to based upon some certain differences, we can create the flood zone delineation map for the lower delta region. So this work is under working stage, and we can identify the high and low hazard and the risk zone along the delta plain. So this has been shown for the Mahanadi River basin. So the next is how to learn. So the learning or record-breaking event. So it is a kind of a big data and a small data kind of problem. So we can have a number of meteorological observations. It can be very high observation, it can be limited observation as well. But everything is not visible. So we have to see which of the extreme is actually creating an impact. So the example here is the annual maximum water level and the peak river discharge. When you consider the central state, so here you can see the river discharge and the coastal water level. When it is at a mean climatic state, that at the mean level, it does not create an impact. But whatever is more important is to see at the extreme level. So we can calculate the upward dependency at the extreme level. So at the mean state, it may not create an impact, but at the extreme state, it has a considerable impact. So that can be estimated using the scale dependency result. So here, this is the climate rider 1 and the climate rider 2. So this is the mean climatic state, and here it is at the scale level. So we are mostly interested at the scale level. So that leads to the block 1 event. The data we are working for probability density function at the tail. So that creates the most impact. So our to identify this kind of event and the predictability of this event. Now, so how the heat waves and droughts are interlinked? So this is the example of the Indian heat wave condition, 2015 record-breaking heat wave condition, and it will see the events, the historical events from the 1986 to 2015. So over the past 30 years, so in all years we have certain kind of drought. So how to identify this region with more drought zone and which region is less drought zone? To identify this, we can make a kind of a frequency analysis, the severity duration frequency analysis. The normal severity duration frequency analysis comes with the exact picture. So we have to exploit the dependency between the two attributes. So first one is the severity and second one is the duration. So based upon the nonlinear relationship between the two attributes, we can actually delineate the severity of the event for certain particular return. The return period here refers to the extent probability that the event is going to reoccur or come in the next couple of years. So we can estimate from this kind of a graph. So multivariate paired extreme events are the events which occur in succession to each other. So the physical association between the driver actually affects the likelihood of the extreme. So here, the multivariate dependency of the single hazard so based upon the severity and the duration. So how the dependency affects the joint rate, those things are going to explain here. So this is at the global level, all the swim gauges were analyzed. The plot is delineated using the standardized runoff index at an accumulation window of 3 months. Now, so these are based upon the latitudinal profile of these gauges. We divide it into 3 different regions: the tropic, subtropic, and the mid latitude. So in the subtropic region, so we can find the stronger dependency within the attribute, and this actually affects the risk occurrence. So because while the dependency affects the risk calculation that I am going to explain in the next slide, and also now in the next phase, I am going to discuss the compound impact of the paired hazard based upon the graph-based relationship. So the graph-based relationship between the high coastal water level and the peak river discharge. So you can see the stronger the dependency. So here we can see the node and the edge. So the nodes are at the side gauge and the river gauge location, and the edges are the dependency, the strength of dependency between the river discharge and the side gauge. So the stronger the dependency, the stronger is the shade, and the weaker dependency shows the lighter color. So here, based upon a graph-based relationship between the high coastal water level and peak river discharge, we can come out the risk factor, how much is the joint risk of the high river flood and the peak river discharge. Now, so coming to the first case, so we delineate 2 different characteristics. So one is the milder drop, another is the extreme drop. So the milder drop we identify using the 10th percentile of the severity and duration, while the extreme drop is delineated using the 90th percentile of the severity and duration. And the risk is calculated so based upon the multivariate character. So that means considering the dependence between the 2 attributes, that is what is the likelihood or the probability of the hazard if we have jointly occurs the severity and the duration, and along with and if they are occurring the independently. So this amplification is calculated so based upon the independence assumption and the dependence assumption. And if we plot logarithmic way, so you will see kind of a as the strength of dependency is increasing, the risk amplification is also increasing. So this is based upon the difference between the 2 attributes, considering the independence and assumption. So larger the value of this power law, we establish the power law relation. So the larger the amplification of the lambda value, so the larger is the risk. So now how machine learning can try to reduce the non-stationarity and big uncertainty. So according to the science paper of overseas data, so as the model in situ and the satellite data is increasing and the loss of data is increasing, and we are moving towards more data intensive data is not usable. So part of the data is actually in use, but other parts we can just discard it. So for example, also what is the trend in the data, so that actually affects the risk calculation. So here you can see, so this is the mean climatic state, so where it is the bell shaped as a normal distribution. But when we move towards the extreme case, so that means there is a shift towards the mean or the variance of the distribution. So that will be reflected by the locational and the scale and the shape shift of the distributional property. So this is one of the examples that we did for the Mahanadi River basin. So this is in all cases you can see there is a increasing trend of the river flood. So this river flood is calculated based upon the annual maximum discharge. So if there is a 30 years data, so this 30 years data, all data is not visible here. So we are only extracting the annual maxima. That means for each year there is a maximum. Upon that, the flood trend is calculated. And now, also we found there is a kind of a decadal shift. That means that basin, so there is a lesser operation in the flood rate as compared to the lower and the middle basin. So that means all data is not usable, but the obtained probability data is of use for the predictability of the extreme event. So now moving to how we can bring the physics as well as data to extract the meaningful information. So here we calculated the timing of the class at the Mahanadi River basin. So here we can say, so this is again the sampling was done using the annual maxima event. So most of the flag occurring during the late monsoon period in the August and the September. But in India, it is the monsoon time is between June to September. So that means the late occurring timing of the flag is mostly concentrated in the late monsoon season. Now there is a stronger positive association between the flag timing and the catchment percent. So that will help with the predictability of the flag. So here we calculated the catchment percent using the soil moisture. So what is the value of the soil moisture? So with zero is the date of occurrence of the flag, and proceeding to this, we calculated the soil moisture based upon the daily soil moisture database available by European Space Agency. And you can see at preceding date, so more than a month, we have a stronger positive association between the soil moisture, the basin average soil moisture, and the timing of the flood. So the indication that the memory of the soil moisture that affect the flood. So this can be a very useful information and used in the flood forecast model development. Now coming to the non-stationarity and the deep uncertainty. So the weather is actually an initial value problem, and the climate is actually a post-boundary value problem. And the decadal projection lies between the two. So it can be 10 to 15 days or a week of length. So in the decadal projection, so how we can partition or how we can quantify the uncertainty of different models. So if we see the climate model output, there are different realization and the different climate models. So for each climate model, there will be again a multiple realization. So that builds up the internal climate variability or the regulatory uncertainty component. For the decadal projection, it is the regulatory uncertainty, so that has a significant role. And for the end of the century, it is the model spread, so that impacts the larger part of the uncertainty. So this is an example of the global as well as North American and certain cities. climate variability. But for the precipitation, you can see for the global land as well as the regional land, it is, for example, in Phoenix or Seattle or New York, it is actually the internal climate variability, so that has the significant role of the uncertainty quantification of the extreme. So now, to consider these things, how we can quantify the uncertainty of the surface because of the summer extreme and the warmer spring temperature. So this study was done in the United States, as in the beginning slide I have explained. So we quantify the water stress using the newly developed spring water stress index. So that was developed using we have developed in a part of this research. So here we identify around this index. So the surface water we are in the descending order, and the warmer spring temperature we are in the ascending order. And based upon these two index, we came up with a joint trend. And so this is the rank-based index. And once we calculate the probability of this for each point, now it is not easily interpretable. To make it interpretable, we did a standard normal transformation of zero mean and one standard deviation. So based upon the how much deviation from the normal, so the normal is denoted with a zero, the risk factor can be identified. The higher the SWSI, that means the higher risk of coinciding with high spring temperature and the low runoff. So using this, we identify some of this risk zone. So this is the map. So this is the historical period. So here you can see there is not much yellow region. So the yellow region is showing the water stress level. So this is between 0 to minus 0.5. This is not much risk. This is the present day condition. But in the future condition, between 2026 to 2025, so you can see at the central region we have the higher risk. So that is the stress level goes more than minus 1.5. So these calculations were performed using more than 300 climate model realization run, considering the internal climate variability as well as the model structural uncertainty. So here, the big data can play a big role. Big data of the machine learning can play a big role to understand the partitioning of the uncertainty. But in this case, we put the entire model together. So all the models, considering the all internal climate variability run as well as the model structural uncertainty, so everything we put together. But this can be further improved, and the quantification of the uncertainty could be possible depending on the model runs. Now, the last part I'm going to explain. So the projection of the compound plot. So here the compound plots are the plot so that things can take place when the river, coastal, as well as the precipitation induced plot. All these plots, the low-lying area, the coastal area, play a major role. And the recent example is the case of the cyclone C3 RDR. So that bring a lot of water at the coastal area. So because of the coastal flooding, for example, in Bihar region, and also in England also, they had a huge failure because of the fluvial and the fluvial flood. So the projection, how to project this kind of a uncertainty for the flood forecasting mechanism. There are various sources of uncertainty to project this phenomena. So first one is the forcing data uncertainty. So the uncertainty can stem from the Twitter climate model that has been used to project this. And the numerical model thing, the suite of hydrologic and the hydrodynamic model run, and the bias correction, the pre and the post bias correction method. So all these actually work together get the hazard delineation. The last one also is the sea level rise. So sea level rise is one of the major challenges as a contributor of the coastal flood risk. So now, considering all these sources of uncertainty, how the quantification can be possible. So the example we took as the European flood. So here the observed data was from the 1981 to 2005, so that we considered. And the paired extreme event was analyzed by taking the annual maximum to coastal flood and the river peak discharge within a week of occurrence of the annual maximum flood. So these locations, we can say the river gauge location, and we identified the strength of dependence along this plane. And so this is the observed data trend. Now, eliminating this trend for the projected time window is again a challenge. So for this, we analyze the suite of the regional climate model run. So and that was coded using the Day3 hydrodynamic model. And the river flood is estimated using one of the global hydrological model. And we can see we can get to some extent the dependent strength is established.
Hello. Hello. Hello.
Hello,
Hello.
Dr. Ganguly.
Hello. Hello.
Dr. Ganguly, you're not audible.
Hello. Madam, are you able to hear me?
Yeah, you're audible, Amit.
Yeah, actually, suddenly this phone, this voice stopped coming.
Oh,
So I will call her again. Just disconnect.
yeah, it's really difficult.
Her phone is actually mobile network is getting problem. So I think it's coming engage.
I think Mr. Aruna ma'am is talking to her, I think so.
Okay.
Yeah, madam, it is on.
Hello.
Yeah. Is it audible?
No, ma'am, it is not audible.
I will call her. You can disconnect.
Yeah, she is on my phone.
So you can disconnect. I will connect again.
Pardon? No, she is speaking on this phone, on my number.
Yeah,
Ma'am,
so
but from your phone, voice is not audible actually.
so you can disconnect, madam. I will call her.
Okay, okay.
So I am unable to connect. Maybe on chat we can take questions and so
She's calling to Amit. Madam is calling to you shortly.
yeah, I think there is some network problem. Maybe from my side or maybe from we don't know. So
I was giving one suggestion that Madam is going to record the session at her end, and then somehow we can think later that how we can communicate to participants.
yeah, we can upload on the YouTube if required on a
Yeah,
separate. Maybe now we can take questions
that's
on
what I
this.
was saying, Madam.
Yeah.
I was saying same thing to
Ma'am,
you.
this is what we received a comment from Karthikeyan sir as well, that he is requesting that to separately conduct a session by ma'am. So I think recorded session help everybody.
Because the voice was very low, na?
Very low, yes,
Participants,
ma'am.
and she prepared so well, so
Mhm.
exhaustive slides.
Yeah, so
But
maybe she can record it
unfortunately,
and send to us, and then we can put on YouTube
yes,
because already that
that's a good
channel
solution.
is there. Yeah.
Yeah, Madam, we are audible to you, I guess. So that's the suggestion from all committee members. Yeah. Yes, Madam. So you please record at your end, and then you send it to me, and then we'll upload on YouTube because we are already broadcasting on YouTube.
And we can take some questions on chat.
Yeah, yeah. So Ajay, can you give? You took some questions? No questions actually. I don't know whether participants were able to understand or
No,
not.
no problem.
That's also. So please
So we should
record your session at your end and send it to us. So she is recording at her end, and then she will be sending after 1.5 hours, as soon as she finishes.
Sure.
So anyway, our valedictory was scheduled at 4:30. Let me call chief guest and end this session. So meanwhile, let's do valedictory. Dr. Ratnaparki, Amit, Neha, and Om Prakash.
Yes, yes.
Yes, we can go
I
ahead.
just call my chief guest. I just check whether he's free or not, because I have given time 4:30. Participant, please wait. Our Dean R&D, IIT Indore is joining shortly. He is in office and fortunately he's free right now. So he's joining quickly. So let us start our valedictory after some time. And in case participant, any feedbacks you can put in chat box, any quick inputs. However, you already filled feedback form regarding sessions and all. But if you want to give some quick comments, you can write in chat box and our volunteers will copy here in the WebEx.
I think there are some
Ma'am,
comments.
we get a comment that it was a highly informative workshop with speakers from diverse backgrounds. I highly appreciate if I can receive the presentation hands-on material for practice and to revisit the information. We'll look forward to many such more workshop with the student practice sessions.
So yes, this is the first workshop under this NSM funds, and we received funds in March end, and it's very short of time. We prepared, we planned it, and Amit suggested us we can do this thing. And that time pandemic was on peak. Then we have decided as soon as that pandemic slow down, we'll do that. So we planned it during this mid of July, and thank God that. Now things are comfortable and participation is very good. It is more than 2000. But what is disappointing me, registration was very much more than 2000. But when I was looking at the YouTube, every day number is not crossing 200. So real participation was 200. Maybe at random participants are coming as per their interests. Continuously they are not attending. But anyways, it's a good return to us, and we are definitely planning number of workshops under NSM, and obviously because it's a big group, we are in touch with each other and we are planning more things under NSM. And as far as IIT Indore is concerned, there are many short-term such courses are going on, and this is first workshop on high performance computing in IIT Indore, but many more will keep on coming because in IIT Indore 3 other colleagues also got funding from NSM. So probably they are also planning to do something under this high performance computing in near future. So Dr. Palani joined, our Dean R&D. Able to hear us, Dr. Palani? So yeah, Dr. Palani, thanks a lot joining so quickly. And he's in office.
So I think it's a very nice.
So welcome, Dr. Palani, as a chief guest. Neha, please. So
yeah. Very good afternoon, Professor Palani. And good afternoon to everyone, to one and all present here. We are moving ahead to the end of the workshop and towards the valedictory session. We have with us our honorable chief guest, Professor I.A. Palani, Dean R&D IIT Indore. I request Professor Palani to share his views on this workshop with all the participants. Over to you, sir.
Thank you very much for inviting me to this wonderful forum. So on behalf of IIT Indore, I give my honorable gratitude to Dr. Milind and Neha and Dr. And I have a great gratitude to Dr. Aruna Tiwari, Madam, because she has been working hard for coming up with such kind of nice funding in this related programs. So I'm happy to be a part of this particular forum. So in a nutshell, if I would like to say, so as if the speakers have pointed out, the importance of agriculture, the importance of advanced technology towards agriculture. So probably you might have got a detailed outcome about these conference. So whenever there is a valedictory is taken into consideration, so we feel that the conference is ending, but actually it's just a comma, so that we need to consolidate what are all the outcomes which we are getting it from the conference, and we should put it in a right form. So that is what my humble submission as a Dean R&D from IIT Indore. So I request Dr. Aruna Tiwari Madam and all the other delegates who are involved in this conference to make a short write-up, so that we will keep this conference website on, and we will just post those outcomes over there, so that whenever some government agencies or some private agencies, when they're trying to take out some of the policies, so our outcomes will be highly helpful for them, or it may also act as a roadmap for creating some policies, etc. So that is an important aspect which I would like to record over here in this particular forum. So I wish many more such programs will be coming. So I know Dr. Aruna Tiwari, she has come up with a very good team. So much more programs are yet to come, and we would be happy to support those particular. Thank you very much for this particular forum. Thank you.
Thank you, sir, for your inspiring words. And surely we will
thanks. One minute, Neha. Just for your kind information, Dr. Palani.
Yes.
That he joined as a guest of honor on first day. He already sent me a mail that please prepare a report on this workshop.
Very nice. Very nice.
And send to me, so that we will make a policy. Will incorporate those things for policy decisions. And in fact, he is heading this thing, NSM thing for with ISC. So same thing you have commented. So we are already under preparation for that report.
Yeah, actually, what I would suggest is, you please prepare a report. So one report you can send it to them. One report let it be on an online platform, and one report you can submit it to our library, so that tomorrow when some students come, it will be easy for them to refer. So, so we should have some kind of repository regarding these outcomes. So that will be helpful for the future. Great, ma'am. That's very nice.
Yeah, thanks a lot.
Thank you.
Please go ahead, Neha.
Thank you, sir, for your inspiring words, and surely we will project our outcomes so that it would be useful for the society and all the aspirants working in this domain. I extend my heartiest thanks to you. Also, I extend a warm thanks to all the participants gathered in this event, and it is such an honor for me to get the opportunity to thank all the dignitaries. On behalf of the organizing team and the collaborating institute, I would like to express my gratitude to all the esteemed delegates and the speaker of the workshop for their presence and contribution to make this workshop a great success. I also extend my hearty thanks to Professor N.K. Jain, Director IIT Indore, Dr. Neeta Khandekar, ICAR ISR Indore, Professor Yajlu Maduri, Vice Chancellor, Mahindra University, Hyderabad, for their extensive support and allowing us to conduct this event successfully. A special thanks to Mr. Amit Saxena, Joint Director, HPC, Medical and Bioinformatics Application Group, CDAC Pune, for providing immense support to make this workshop successful. I must thank the volunteer, Mr. Vikas, Mrs. Suchitra, Mrs. Preeti Jha, Mr. Rajesh Trivedi, Mr. Ajay, Mr. Nilesh, Mr. Saurabh, for working hard for the past few days to make this workshop successful. I congratulate all the participants for their active participation. Thank you everyone once again for making it a great success. Thanks again.
Would like to just share a comments this was a very amazing for the agriculture institute like soybean institute different diverse group from all over India coming together and giving presentations, and this with these interactions we can develop further collaborations for making a big impact in the Indian agriculture sector. So I thank all the IITs, Dr. Tiwari and all the faculty there for giving such an opportunity for everyone to join in these workshops. Thank you very much.
So I think we can see in the chat there are some very good comments from Dr. M. Karthikeyan. He's saying that I really enjoyed every talk and learned a lot. Heartiest congratulations to our guys. So I think he is also there. So sir, can you unmute and say a few words? Dr. Karthikeyan.
Sir, I think he has written.
Thank
Yes.
you.
Yeah, he's there.
I really enjoyed from the beginning till the valedictory, and each and every slide, every word spoken by all the speakers were very nice. I learned a lot. Being a chemist, I learned a lot about high performance computing, quantum computing, distributed computing, starting from microchip till application in agriculture. I really enjoyed. I'm sure everybody enjoyed these talks. Unfortunately, I'm not able to start the camera. I think it's okay. It's the best wishes for the organizers for making this event very, very great success. And I wish you should continue this type of traditional as a tradition, so that many people in the country will get benefited, and eventually it will reach the field from research to field. You made a foundation. Thank you.
Thank you, sir.
I request.
Did you able to hear me?
All the coordinator.
Yes.
Yeah,
Yes,
thank you,
sir.
sir.
Thank you, sir. Thank you so much.
Thank you very much.
Thank you, sir.
Thanks for your kind words.
I request all the coordinator Ajay, Nilesh, Preeti, Saurav, Vikas, please on your camera, because without your support, it won't be possible to conduct such good workshop. We want to thank you.
Saurav, please take a photograph. So now Vikas switched on camera first time. So today morning, my son was saying that this background image is always there, but no one is there. So I told him, Anmol, he was saying, so I told him that he is managing all these networking issues and he's doing his research on the verge of submission of PhD thesis. So I'm not disturbing him. He's doing a great job. Thanks to all the volunteers, Dr. Karthikeyan, for joining all the sessions. So Neha, this is done?
Yes, ma'am.
Yeah.
So
So thanks, Dr. Palali.
Thank you. Thank you.
Yeah. Thanks, Amit.
Thank you. So I think we should formally close it, and we wish that all the
Yeah.
students will take whatever they have
All the
learned, and
participants.
all the participants they will take whatever they have learned and they will apply in their field. Thank you.
Yeah, and for this last session, we are sorry for the last session, and Madam is recording that session and shortly will upload on YouTube. So that way you will not miss that thing.
Okay.
Okay, and for certificates, I think already messages are circulated. Om Prakash, can you tell something about certificates?
Yes,
It is already
certificate
circulated.
we have put the feedback form in description and also in chat box. So I think everyone has filled it. Nilesh, do we have any data regarding it?
Yes, the responses are coming.
Okay.
Just
as we used to see always a YouTube video and we see some positive and negative comment both, but as I can see throughout the session, all the 3 days, we always get appreciated for our session. That's a great thing, great achievement.
So thank you. Thanks all participants.
Thank you so much.
Okay, bye-bye. So let us close the session.
Thank you very
Okay,
much.
bye-bye.